Explore the behind-the-scenes world of fast food giants Taco Bell, Chick-Fil-A, and Burger King. From high-speed kitchens to industrial food preparation, discover how each chain transforms raw ingredients into iconic meals served in minutes. This deep dive reveals the unique systems, technologies, and processes that power some of the most popular fast food restaurants on the planet. For Taco Bell, it all starts with ingredient sourcing. Each core component, beef, chicken, tortillas, cheese, lettuce, beans, and sauces, is handled as a separate production category. Take the seasoned beef, for instance, one of the most widely used ingredients in Taco Bell's product lineup. The ground beef used in their tacos and burritos is not prepared in restaurants from raw cuts, but is instead pre-cooked and seasoned at dedicated meat processing plants. These USDA-inspected facilities receive large quantities of lean beef trimmings from approved slaughterhouses. The trimmings are first ground to a standardized size, then cooked in continuous belt cookers or steam-jacketed kettles, where they are combined with a proprietary spice mix and water. This seasoned beef mixture includes salt, paprika, garlic powder, onion powder, chili pepper, and food-safe thickeners such as maltodextrin or modified cornstarch, which help maintain moisture and consistency during reheating. Once cooked and blended, the meat is rapidly cooled using blast chillers to bring it down to a safe storage temperature, typically under 40 degrees F. It's then sealed into vacuum-packed, food-grade plastic pouches, often in 5 to 10 pound portions, and shipped to Taco Bell locations in refrigerated trucks. Reheating in the restaurant is done via hot water immersion. Staff place sealed pouches of seasoned beef into temperature-controlled water baths or steam tables where they are brought up to a serving-safe temperature of approximately 165 degrees. Once heated, the pouches are opened and the beef is transferred to metal steam pans for assembly line use. This system ensures consistent flavor and safety while eliminating the need for on-site raw meat handling or complex cooking. The chicken used in Taco Bell's items, such as the chicken quesadilla or chicken soft taco, is also pre-cooked and seasoned off-site. Chicken breast or thigh meat is cooked via steam ovens or flame grilling conveyors, chopped into small cubes or shreds, and seasoned with blends that may include lime, cumin, garlic, or smoke flavor. Like the beef, it is packed, chilled, and delivered in vacuum-sealed bags, ready for simple rethermalization in store kitchens. Beans represent another foundational element of Taco Bell's menu. However, the refried beans used in tacos and burritos do not begin as whole-cooked pinto beans in store kitchens. Instead, Taco Bell utilizes dehydrated bean flakes or paste that is shipped in dry form to each restaurant. In-house preparation involves mixing the dehydrated bean base with hot water in large mixing containers. The hydration process usually takes about 30 minutes, resulting in a thick, smooth, refried bean mixture that mimics the flavor and texture of slow-cooked beans without the need for hours of simmering. Taco shells, soft tortillas, and flatbreads used in items like chalupas or gorditas are all factory-produced in massive quantities. Tortilla manufacturing plants produce millions of units per day using high-capacity presses and continuous baking ovens. For crunchy taco shells, corn masa dough is rolled flat, cut into circles, then shaped into taco forms using conveyor-mounted clamps that hold the shells in a U-shape while passing through hot oil fryers. Soft flour tortillas are rolled, pressed, and baked in tunnel ovens before being cooled, stacked, and packaged. All tortilla products are delivered to Taco Bell stores in bulk quantities, often stacked in wax-lined boxes or plastic-wrapped bundles. Shredded cheese, typically a blend of cheddar and mozzarella known as cheddar melt or low-moisture cheese, is also prepared off-site. Dairy plants shred and anti-cake the cheese using potato starch or cellulose, then bag and cold store the product in 5-pound bags. Lettuce and tomatoes are sourced from large-scale produce distributors. Lettuce is pre-shredded and washed in chlorinated water systems before being sealed in bags and shipped cold. Tomatoes arrive diced and ready to use, stored in resealable containers. This product is handled under tight temperature controls to minimize spoilage and maintain food safety. One of the key hallmarks of Taco Bell's food production system is the precise engineering of its sauces and flavor components. From fire sauce to nacho cheese and avocado ranch, each condiment is mass-produced in food processing plants using batch tanks, emulsifiers, and thermal pasteurizers. These sauces are hot-filled into flexible pouches or plastic bottles and shipped to restaurants in cases. The nacho cheese sauce, for instance, arrives in large plastic bags that are reheated in warming trays and dispensed into smaller serving containers or squirt bottles for assembly line use. With all core ingredients delivered and prepared, the in-store operations at Taco Bell are focused primarily on assembly, heating, and final presentation. Kitchen layouts are designed with efficiency in mind. Stations are arranged for maximum throughput, with hot holding units for proteins, refrigerated bins for cold ingredients, and toasting presses or microwave ovens for final heating steps. Each employee is trained to follow strict build charts that dictate the exact weight, portion, and layering sequence for every menu item. Consider the construction of a simple, crunchy taco. An employee grabs a pre-fried taco shell, scoops in 1.5 ounces of reheated seasoned beef, sprinkles on a portion of shredded cheddar cheese, and tops it with shredded lettuce. The taco is placed in a pre-formed cardboard holder or paper wrap and slid down the assembly counter. Another team member may bag the item along with others in the order and hand it off to the customer or delivery system. Each item is constructed in under 30 seconds, often with multiple staff working in tandem to complete combo meals. More complex items, like the Crunch Wrap Supreme or Quesarito, involve multiple cooking surfaces. The Crunch Wrap begins with a large flour tortilla laid on a prep station. A portion of seasoned beef, nacho cheese sauce, a crunchy tostada shell, sour cream, lettuce, and tomatoes are layered precisely. Then the tortilla is folded inward in a 6-sided pattern. The folded wrap is then transferred to a clamshell grill, where it is toasted for 15 to 20 seconds on each side, creating a sealed, crispy exterior that holds all components inside. Timing and temperature control on these grills are essential to ensuring consistent texture and flavor. Items that require melting, like the chicken quesadilla, are prepared on flat-top presses, where cheese and sauce are sandwiched between tortillas and grilled until the inside reaches the right melt consistency. The burrito category includes both cold-rolled and hot-pressed variants, some of which are briefly steamed in microwave units to soften the tortillas for better folding. Each order flows through the point-of-sale system into digital kitchen displays or printed tickets that guide the team through item prep. Digital timers and alarms notify staff when holding times are exceeded. For example, beans and proteins can only be kept in steam trays for a certain number of hours before being discarded. This food safety timing is enforced by on-screen alerts and regular audits. Taco Bell also operates with tight allergen and cross-contamination protocols. Ingredients like eggs and gluten are kept in color-coded bins, and staff are trained to change gloves and utensils when handling allergen-sensitive items. Regular hand washing, surface sanitizing, and utensil swapping are monitored to comply with food safety regulations. Waste management is another component of the behind-the-scenes operations. Ingredient overages, expired pouches, and unsold food must be recorded, discarded, and tracked to help corporate operations refine inventory planning. In larger, high-volume locations, daily food waste is separated by category and used to adjust future order quantities and reduce spoilage. The speed and consistency of Taco Bell service are powered by centralized prep, strict protocols, and kitchen ergonomics. Unlike traditional made-from-scratch restaurants, Taco Bell excels in reassembly-based cooking. Nearly every component is pre-cooked or pre-processed before entering the store, then finished through heating, assembling, and packaging. Distribution plays a huge supporting role. Taco Bell's supply chain is managed by logistics partners who oversee refrigerated warehouses, regional distribution hubs, and real-time inventory tracking. Each store receives multiple weekly shipments in temperature-controlled trucks with organized inventory manifests. Cold goods, frozen ingredients, and dry stock are unloaded and stored according to first in, first out practices to ensure product rotation and freshness. The journey of every Chick-fil-A meal begins at the sourcing stage. The star of the menu, the boneless chicken breast filet, is sourced from select poultry suppliers in the United States. These suppliers raise chickens under strict guidelines that align with Chick-fil-A's specifications for breed, weight, and overall meat quality. The birds are harvested, deboned, and portioned into consistent-sized breast fillets. Unlike many competitors who pre-bread or par-fry their chicken at a central facility, Chick-fil-A's chicken breasts are shipped raw to each restaurant in refrigerated containers. This raw chicken is never frozen, allowing for a level of freshness that the brand believes enhances taste and texture. Each boneless, skinless chicken breast is trimmed and pre-marinated at the processing facility in a proprietary blend of seasonings and pickle juice brine. This marinade is designed to infuse moisture and flavor deep into the meat, enhancing its juiciness and imparting the slightly tangy profile that Chick-fil-A fans recognize instantly. Once marinated, the raw, unbreaded fillets are vacuum-packed and shipped cold to the restaurants on a tightly managed logistics schedule. At the store level, food preparation is more involved than in many other quick-service restaurants. Chick-fil-A maintains what could be called a semi-scratch kitchen model. That means that while certain ingredients are prepared off-site, a large portion of the cooking, including the breading, frying, and assembly, is done entirely in-house, by hand, and to order. Once the marinated chicken arrives at the store, it is stored in walk-in refrigerators until needed. When an order is placed, staff members retrieve the raw fillets and manually bread them in real time. This process occurs at designated breading stations. Employees take the chicken from the cooler, dip it in a liquid egg wash, and then dredge it in a dry flour mixture that includes a carefully balanced blend of spices, paprika, black pepper, salt, and other proprietary seasonings. The breading is done using a method known as pressure packing, where the breading is pressed firmly into the meat using a specific motion and timing to ensure even coating and adhesion. Excess flour is shaken off, and the chicken is immediately sent to the fryer. Chick-fil-A uses pressure fryers, which are similar in design to commercial deep fryers, but operate under sealed, pressurized conditions. This allows the chicken to cook faster and more evenly while locking in moisture. Each fryer basket is lowered into preheated oil, usually peanut oil, selected for its high smoke point and clean flavor, and cooked at a consistent temperature. The pressure fryer ensures the chicken reaches a safe internal temperature of 165 degrees while forming a crisp, golden brown crust that adheres tightly to the fillet. The total cooking time is typically around 4 to 5 minutes, depending on the thickness of the chicken. Meanwhile, the buns for the classic Chick-fil-A sandwich, soft, white hamburger buns, are stored in sealed bags and toasted on a flat-top grill or vertical toaster just before serving. Each bun is lightly buttered, toasted until golden brown, and then used as the base for sandwich assembly. A single dill pickle slice, or sometimes two, is added directly to the bottom bun before the hot, freshly fried chicken fillet is placed on top. This simplicity is intentional. The standard sandwich contains no sauce, no lettuce, no tomato, just chicken, pickles, and bun. The clean flavor profile helps highlight the taste of the seasoned chicken. For other menu items, such as the spicy chicken sandwich or deluxe versions, the process is similar, but may include spicy seasoning in the breading or added toppings like lettuce, tomato, and cheese. These variations are all built on the same foundation of freshly breaded and fried chicken. In addition to sandwiches, Chick-fil-A's menu includes items like chicken nuggets and chicken strips, which are made from the same chicken breast meat but cut into smaller portions. Nuggets are breaded and fried using the same process as the sandwiches, but are cooked in separate baskets to ensure optimal timing and doneness. They are drained, portioned, and served with a variety of sauces, including Chick-fil-A sauce, Polynesian, barbecue, and more. These sauces are mass-produced in centralized facilities and shipped to stores in portion-controlled packets or squirt bottles. One of the most labor-intensive and visually distinctive products is Chick-fil-A's waffle fries. These are made from US-grown potatoes, typically russet or similar varieties. The potatoes are processed at off-site facilities where they are washed, peeled, and sliced using a specialized corrugated blade that cuts the signature waffle pattern. The fries are par-cooked, lightly fried or blanched, then frozen for shipment. At the store level, fries are deep-fried in vegetable oil until crispy and golden brown, then salted and served in paper fry cartons. Timing is critical, as fries can quickly lose texture if overcooked or held too long under heat lamps. Salads and wraps are also a major part of the menu and are made fresh daily in each restaurant. Prevent cross-contamination between raw and cooked products. Chicken is handled with gloves and dedicated tongs. Refrigeration zones are monitored with temperature logs, and hand washing is mandatory at regular intervals throughout each shift. Inventory is tracked digitally using integrated systems that forecast usage patterns based on sales data. Deliveries arrive several times per week in refrigerated trucks managed by regional distributors. Ingredients are unloaded and placed into designated storage zones. Dry goods in pantry racks, dairy in walk-in coolers, and frozen items in freezers. First in, first out procedures are strictly followed to ensure freshness and minimize waste. While Chick-fil-A emphasizes hospitality and service, its operational core is deeply industrial. Behind the smiling team members and friendly service is a kitchen run with the efficiency of a well-oiled machine. Staff are trained for weeks on food safety, equipment handling, and assembly line execution. Managers use real-time kitchen display systems to track order times, ingredient usage, and customer wait durations. Every Burger King sandwich begins with one core ingredient: beef. The signature flame-grilled beef patties used in Whoppers and other burgers are produced off-site in USDA-approved meat processing facilities. These patties are made from ground beef sourced from large-scale cattle operations, typically using a blend of trimmings that provide the right balance of fat and lean meat for flavor and texture. Burger King uses frozen beef patties that arrive in individually separated stacks, typically flash frozen immediately after being formed and shaped at the plant. The patties are not seasoned before shipping. Instead, they rely on Burger King's flame grilling process to impart their unique smoky flavor. Each patty is shaped to standard specifications, precise diameter, and thickness, to ensure even cooking across various store locations. Once frozen and packed, the patties are delivered to Burger King restaurants in refrigerated trucks, along with other temperature-sensitive ingredients. The distinguishing feature of Burger King burgers is the use of a flame broiler. Unlike griddle-based fast food systems that fry patties on a flat top, Burger King uses a gas-fired conveyor broiler. This piece of equipment features metal grates that carry raw, frozen beef patties across an open flame. As the patty travels down the conveyor, the bottom is seared by the grate, while flames rise through the spaces to cook the surface. This creates the familiar grill marks and smoky char flavor that Burger King promotes as flame grilled. The time, heat, and flame intensity are precisely calibrated for each patty size, and sensors ensure consistent performance throughout the day. After cooking, the hot patties are held briefly in a heated chute before being placed on sandwiches made to order. Holding time is carefully limited to preserve moisture and flavor, and any unused patties are discarded after a preset interval, typically no more than 10 minutes. Meanwhile, buns are sourced from regional bakeries that contract with Burger King. These suppliers follow detailed specifications for bun size, density, color, and sesame seed coverage. Burger King buns are delivered in plastic bags to each store and kept in dry storage until use. Before assembly, buns are toasted using vertical toasters or clamshell-style contact toasters that give the bread a lightly browned, crisp surface. This toasting step is important not only for flavor and texture, but also to prevent the buns from becoming soggy when layered with hot ingredients. Vegetables like lettuce, tomatoes, and onions are delivered pre-washed and pre-cut by produce suppliers, reducing the amount of prep work required in store. Iceberg lettuce is shredded into fine strips. Tomatoes are sliced into thick rounds, and onions are cut into rings. These items are packed into food-grade containers and stored in the walk-in cooler. In the kitchen, they are portioned into smaller bins and placed on refrigerated make lines for quick access during sandwich assembly. The Whopper, Burger King's flagship sandwich, is a prime example of this orchestrated system. The build begins with a toasted sesame seed bun, followed by a cooked beef patty fresh from the broiler. The bottom bun gets a layer of mayonnaise, followed by the patty, lettuce, tomato, sliced onions, pickles, ketchup, and the top bun. Each ingredient is placed in a specific order to control how the sandwich holds together and delivers flavor with each bite. The finished sandwich is wrapped in a branded wrapper and handed off to the customer, typically in under a minute from the time it was ordered. Sausage patties and bacon strips are pre-cooked at the factory and reheated in microwave ovens or clamshell grills. Croissants, biscuits, and muffins are toasted or warmed before assembly. The result is a hot, made-to-order breakfast sandwich built to brand specs. All ingredients in a Burger King kitchen are stored and rotated using first-in, first-out inventory systems. Refrigerated and frozen goods are kept in walk-in coolers and freezers, while dry ingredients, such as condiments, packaging, and buns, are stored on wire racks in designated stock areas. Each location receives scheduled deliveries several times per week from regional distribution centers that consolidate goods from multiple suppliers. In terms of food safety and quality assurance, Burger King enforces strict operational guidelines. Cooking temperatures are continuously monitored with digital thermometers. Meat must reach designated internal temperatures, generally 165 degrees for chicken and 155 degrees for beef, before being served. Holding times for cooked items are carefully tracked using timers. Once expired, items are discarded to ensure freshness and safety. Sanitation plays a crucial role as well. Fryer oil is filtered and replaced regularly to prevent flavor degradation. Food contact surfaces are sanitized between shifts. Employees are trained to change gloves frequently, wash their hands according to standard procedure, and avoid cross-contamination between raw and cooked foods. Temperature logs are maintained daily, and stores are audited by corporate teams for compliance. Digital systems also support the kitchen operation. Each order is displayed on kitchen monitors that guide employees step by step through preparation. Timers indicate how long each cooked item has been held. POS systems automatically update inventory data based on sales, helping managers reorder stock as needed and minimize food waste. Packaging is another important piece of the Burger King operation. Sandwiches are typically wrapped in branded wrappers that are color-coded by product type to make identification easier. Burgers may also be served in clamshell boxes or paper sleeves, depending on local standards. Fries are packed into branded cartons, and combo meals are bagged in paper bags, along with napkins, straws, and condiments. All packaging is designed for speed, functionality, and heat retention. To keep up with changing tastes and competition, Burger King frequently introduces limited-time offerings. These often involve new flavor combinations, special sauces, or modified versions of existing sandwiches. When an LTO is launched, stores receive new ingredients, updated build charts, and promotional materials. Staff are trained on the new product and briefed on its preparation and assembly. Once the promotion ends, the remaining stock is used up or removed from the line. It all begins long before a Dunkin' Donut ever meets a customer's lips. The journey of a factory-made Dunkin' Donut starts in massive industrial facilities engineered specifically for high-throughput baking and frying. Unlike the fresh, hand-prepared donuts in local bakeries, the factory-produced donuts that supply regional distribution centers or large retail outlets are the result of a tightly choreographed sequence of automated, mechanized operations, each designed to maximize consistency, food safety, and output volume. The core ingredients of a Dunkin' Donut seem simple: wheat flour, sugar, yeast or chemical leavening agents, eggs or egg solids, milk derivatives, oil, and water. But each of these components must meet stringent specifications. The wheat flour is typically sourced from large milling operations and arrives at the factory in bulk pneumatic tankers. Once offloaded into giant silos, it's carefully monitored for protein content, moisture, and particle size. These parameters are crucial as they directly affect gluten development, dough elasticity, and fry stability. The sugar, often in fine granulated form, is similarly delivered in bulk and stored in temperature-controlled hoppers to prevent clumping. The yeast, which may be active dry or instant, is carefully handled to maintain viability. For cake-style donuts, chemical leaveners such as sodium acid pyrophosphate and baking soda replace yeast, requiring exact dosages to control rise, texture, and batter pH. Liquid ingredients like water and milk concentrates are pumped from stainless steel reservoirs through filtered lines. Egg solids, whether powdered or liquid, are introduced via sealed containers to reduce contamination risk. At the heart of the process is the dough preparation system. In a typical yeast-raised donut line, a computerized batching system automatically dispenses pre-weighed quantities of dry and wet ingredients into a horizontal spiral mixer, usually a high-capacity unit capable of mixing several hundred pounds per batch. This mixer blends the ingredients through a timed, multi-speed cycle, a slow initial mix to hydrate the flour, followed by a high-speed kneading phase to develop the dough's structure. Temperature probes ensure the dough reaches the optimal final mix temperature, often around 78 to 82 degrees. Any deviation can alter fermentation speed and finished product quality. Once mixed, the dough is transferred, either manually in smaller setups or via automated dough elevators in large-scale operations, to intermediate proofing cabinets. These are large chambers that maintain a warm, humid environment, typically around 90 degrees Celsius, with 85% humidity. The dough rests here for 30 to 45 minutes, allowing initial yeast fermentation to begin. This resting period improves extensibility and relaxes the dough for sheeting. From the proofing cabinet, the dough moves to the sheeting line. Here, massive rollers flatten the dough to a precise thickness, often controlled by laser-guided sensors. A conveyor belt feeds the dough through a series of increasingly fine rollers, each pressing it thinner until it reaches the exact gauge required for donut formation. Dusting flour is automatically sprinkled to prevent sticking, and scrap management systems collect unused dough trimmings to be reprocessed in future batches. Next, the formed dough sheet moves to the rotary cutter station. This is where the signature donut shapes come to life. Custom-designed rotary dies stamp out rings, holes, or specialty shapes like filled bars or seasonal themes. Each cutter is precision machined to minimize dough stress, ensuring even fry results. A vacuum system gently lifts and removes cut donuts from the scrap dough matrix, depositing them onto another conveyor in perfect alignment. These unbaked, shaped donuts are then transferred to the final proofer, a massive multi-tiered system that can resemble a vertical carousel. Moving slowly through this enclosed environment, the donuts are proofed for anywhere from 35 to 60 minutes, depending on product type and yeast activity. This is a critical phase. The dough expands, air cells develop, and the signature light texture of a yeast donut forms. Relative humidity and temperature are tightly regulated to promote even rising. Once proofed, the donuts enter the fryer. This is one of the most visually captivating moments in the factory. Rows upon rows of pale, risen dough transforming into golden brown perfection. Industrial donut fryers are long, shallow troughs filled with high-stability frying oil, typically a blend of soybean or palm oil designed to withstand high temperatures without breaking down. The donuts enter via an automated conveyor that gently lowers them onto the surface of the hot oil, held between 350 to 375 degrees. Floating racks or submerged mesh baskets keep the donuts evenly spaced and ensure uniform frying on both sides. The donuts are flipped halfway through using automated paddles or turning bars, so each side receives equal exposure. Fry time is typically 90 to 120 seconds per side for yeast-raised varieties. Throughout the fryer, oil filtration and replenishment systems remove debris and maintain oil quality, critical for flavor, texture, and food safety. After frying, the donuts move onto a draining belt where excess oil is wickered away using absorbent conveyor surfaces or air knives. From there, they transfer directly to a cooling tunnel, an enclosed, climate-controlled conveyor that gently brings the donuts down to ambient temperature. This cooling phase, usually lasting 8 to 12 minutes, stabilizes the structure and prevents condensation before glazing or filling. Now comes one of the most iconic steps: glazing. The donuts pass beneath a cascading curtain of warm glaze, typically made of powdered sugar, water, and stabilizers like corn syrup or mono and diglycerides to ensure sheen and viscosity. The glaze is held at precise temperatures, around 105-115 degrees Fahrenheit, to allow smooth coating without excessive dripping. Any glaze runoff is collected, filtered, and reused within quality limits. For filled donuts, a separate line handles injection. This is a precise, high-speed process where each donut is clamped and filled through nozzles that inject jelly, cream, custard, or other fillings. Volumetric pumps control exact fill amounts, typically between 15 to 25 grams per donut, to ensure uniformity. The timing of this step depends on whether the donut is glazed before or after filling, a decision made based on the type of coating or desired product appearance. Topped donuts, such as Boston cream or chocolate frosted, pass through enrobing units or individual depositor stations. These machines spread or pipe icing onto the surface, using rotating drums or mechanical arms to achieve even distribution. Sprinkles, nuts, or other toppings may be applied via shaker systems or robotic garnishing heads, with vacuum sensors ensuring no foreign objects are introduced. Once coated, the donuts continue on conveyors to the packaging area. Here, an optical vision system inspects each unit for shape, color, topping placement, and fill integrity. Defective products are automatically rejected and diverted for analysis or disposal. The acceptable donuts proceed into robotic tray loaders or auto packing machines, For bulk shipments, donuts may be arranged in plastic trays stacked into crates. For retail packs, form-fill-seal systems wrap donuts in individual or multi-unit blister packs using heat-sealed film. Each packaged unit receives a date code and product identifier via inkjet printer or laser etching. Metal detectors and X-ray scanners stand guard just before final packaging to catch any foreign materials, from metal fragments to hard plastics. At this point, the product has passed through over a dozen safety checks, far more rigorous than what a local bakery could feasibly achieve. Before leaving the factory, pallets of donuts are weighed, logged, and tagged with RFID labels for inventory tracking. They're stored in temperature-controlled staging areas until trucks arrive. Distribution fleets, often operated by third-party logistics firms, are designed to transport the donuts quickly to regional warehouses or direct-to-store delivery networks. Because many factory-made donuts are frozen for extended shelf life, refrigerated trucks or freezer compartments maintain ideal storage conditions throughout transit. Once at a distribution center or store, the donuts are thawed if necessary and either resold in packaged form or used to stock fresh counters in Dunkin' outlets. Some outlets may perform final finishing touches, like adding fresh glaze, sugar dusting, or customized toppings. But the bulk of the preparation has already occurred at the factory, where industrial consistency reigns supreme. Before a Subway sandwich ever reaches the customer's hands, its journey begins far from the store counter, in sprawling, high-efficiency food manufacturing plants that are responsible for producing machines that elongate them into the familiar Subway sandwich roll shape. Automated flour dusters and non-stick belts ensure smooth passage through the shaping process. For breads with toppings like oats or cheese, the dough passes under a rolling applicator or static sprinkler before entering the next proofing stage. The proofing phase is critical. Dough pieces are placed onto pans and loaded into an industrial proofer, a large, climate-controlled chamber with tiered racks or chain-driven carriers. Inside, the bread rises for 45 to 60 minutes at around 90 degrees Celsius with high humidity. Dough height, elasticity, and fermentation rate are monitored using sensors or inline imaging to guarantee uniform rise. Once proofed, the dough pans move into the par baking ovens. These are tunnel or rack ovens heated to approximately 420 degrees. The bread bakes for about 8 to 10 minutes, enough to set the structure and crust, while preserving enough internal moisture so it can be finished baking in store. After baking, the loaves are cooled in ambient air tunnels before being packaged. Packaging is a delicate process. The cooled loaves are inserted into specially ventilated film or bulk freezer trays. Modified atmosphere packaging may be used to extend shelf life and prevent freezer burn. All packaging is date-coded, labeled with batch tracking, and sent through metal detectors or X-ray systems. Then the bread is quickly frozen in blast freezers that bring core temperatures below zero in under 90 minutes, preserving quality for shipment. While the bread is handled this way, meat and poultry ingredients follow a parallel but very different industrial route. Subway's deli-style meats, turkey breast, ham, roast beef, and chicken strips are cooked, sliced, or formed in specialized meat processing plants. These facilities receive USDA-inspected raw proteins that are boned, trimmed, and cleaned under strict sanitary guidelines. The raw meats are portioned, tumbled, and marinated with Subway's proprietary brine formulas, which often include salt, phosphates, sugar, and flavorings. In the case of chicken strips or patties, the meat may be fully cooked in steam ovens or grill presses, then flash frozen to lock in moisture. Roast beef and turkey, on the other hand, are typically cooked in steam ovens or combi ovens that simulate traditional roasting while maintaining high throughput. Once cooked, the meats are cooled using spiral chillers or glycol plate systems, then sliced on high-speed rotary slicers for uniform thickness. These slices are stacked and portioned by weight using automated weighing machines, then sealed in vacuum pouches or controlled atmosphere trays. Each portion is sealed with batch coating and passed through inspection systems before being packed into cartons and frozen for distribution. Cheese slices, Swiss, American, provolone, and pepper jack, are produced using high-speed forming and slicing systems. Cheese blocks are first melted down, then reformed into large sheets which pass through slicing blades and portion conveyors. Anti-stick sheets are often placed between slices, and stackers organize the cheese into count-specific bundles, each packaged under vacuum or gas-flushed atmospheres to preserve shelf life and prevent molding. Vegetables such as lettuce, tomatoes, cucumbers, onions, and green peppers are not grown in factories, but they do undergo industrial preparation before arriving at each store. Lettuce, for example, is harvested, washed with chlorinated or ozonated water, and shredded in high-speed slices. Tomatoes are cleaned, visually inspected, and machine sliced before being layered between food-safe pads that prevent bruising during shipping. Onions are peeled, sliced, and packaged in gas-flushed bags to reduce spoilage and preserve freshness. All vegetables are packed in refrigerated, ready-to-use formats and delivered through cold chain logistics to ensure they remain crisp and safe for consumption. Subway's specifications for produce are among the most rigorous in the QSR industry, often requiring vendors to perform multiple microbial tests before product release. Sauces, ranch, chipotle Southwest, mayonnaise, mustard, sweet onion, and many others are made in liquid processing plants that function much like beverage or dairy factories. These facilities handle emulsion preparation in large mixing tanks fitted with high-shear homogenizers. Ingredients like oils, water, spices, thickeners, and preservatives are blended under vacuum to ensure air-free, stable emulsions. The sauces are then pumped into sterile filling machines that dispense measured volumes into squeeze bottles, bulk pouches, or portion cups. Heat sealing, tamper-evident caps, and nitrogen flushing preserve shelf life. Every component, from bread to sauce, is designed with logistics and final assembly in mind. Once all the parts are complete, they're loaded onto pallets, sorted into refrigerated and frozen shipments, and transported to Subway's distribution centers. From there, truck routes are carefully scheduled to ensure timely delivery to thousands of store locations. All products are scanned, tracked, and recorded during shipment, ensuring cold chain integrity and traceability from plant to sandwich counter. Inside the store, the staff becomes the final assembly line. Each morning, the frozen bread dough is thawed and given a second proof before finishing its bake in the store's convection ovens. Meats are defrosted and held in refrigerated bins, vegetables are placed into prep trays, and sauces are opened and loaded into squeeze bottles. Sandwich artists follow precise build sheets and portioning guides to ensure a consistent experience for the customer. Even at the store level, there are echoes of the factory's precision. How many ounces of lettuce per 6-inch sandwich? How many slices of meat? What angle to cut the bread? It all comes back to what was engineered upstream. Without the highly standardized processes in the manufacturing plants, the in-store experience wouldn't feel as predictable and familiar across the world. The industrial journey of a Chipotle meal begins with ingredient sourcing. Chipotle is known for its emphasis on food with integrity, which means that much of the upstream processing is tightly controlled, even before the factories get involved. The chain sources meats that are often antibiotic-free, pasture-raised, or sustainably farmed. These meats arrive at centralized processing plants, some Chipotle-operated, others contracted to third-party co-packers, with exacting specifications. Take chicken, for instance, one of Chipotle's most popular proteins. Whole chicken breasts and thighs are delivered from certified suppliers in refrigerated transport and immediately placed into cold storage bays at the processing facility. These facilities are equipped with advanced sanitation systems, including antimicrobial entry zones and HEPA-filtered air circulation to maintain a sterile environment. The chicken is deboned, trimmed of excess fat, and portioned into standardized sizes using automated cutters. Optical sorters with high-speed cameras and laser detection systems inspect each piece for defects, bone fragments, or inconsistencies. After cutting, the chicken moves into industrial tumblers or vacuum mixers where it is marinated. The marinade consists of oil, spices, garlic, citrus juices, and chipotle pepper, all pre-mixed in large blending tanks. These tumblers are designed to evenly coat the chicken while tenderizing it, using a slow rotational motion that lasts anywhere from 20 minutes to several hours, depending on the specific formulation. The chicken is then sealed into vacuum-packed pouches or bulk containers and flash chilled. In many cases, the chicken is shipped raw to Chipotle locations, where it is grilled fresh daily. However, in higher volume markets or during peak operational periods, some portions may be pre-cooked using commercial-grade combi ovens or grill presses inside regional commissaries. These ovens are steam-injected and heat-distributed, ensuring that the chicken reaches internal temperatures of 165 degrees without losing moisture. After cooking, the chicken is cooled through rapid chill spiral systems that reduce the temperature below 40 degrees in less than 90 minutes, in compliance with USDA food safety standards. Now let's move to beef, specifically the barbacoa and steak options. These are handled in meat facilities equipped to manage tougher cuts like shoulder clod or round for barbacoa, and sirloin or top butt for steak. The barbacoa beef is typically seasoned, seared, and slow cooked in massive steam kettles or pressurized braising tanks. These tanks operate on programmable logic controllers that maintain precise temperatures and cook times, allowing the meat to tenderize while absorbing the bold, chipotle, and cumin flavors characteristic of the dish. Once fully cooked and shredded by automated paddles, the barbacoa is portioned into pouches and vacuum sealed. It's then rapidly frozen using cryogenic tunnel freezers, often with liquid nitrogen or CO2, to preserve texture and moisture content. Steak, on the other hand, may be seared and sous vided, then chilled and packaged for final grilling in store, allowing for that signature charred flavor upon finishing. Beans, both black and pinto, are another central component of Chipotle's offerings, and their factory preparation is highly systematic. Dry beans are received in bulk sacks and stored in silo bins, where they undergo cleaning, sorting, and rinsing. Industrial bean cookers, large rotating steam kettles or pressure vessels, hydrate and cook the beans using temperature and pressure sensors to ensure that every batch hits the ideal softness and moisture level. Chipotle's beans are often seasoned with bay leaf, garlic, cumin, and salt, and held in stainless steel jacketed tanks for blending. After cooking, beans are cooled, portioned into food-safe containers or sealed bags, and transported under refrigeration to stores, where they are reheated and seasoned further before serving. Some regional commissaries may do the final seasoning step in-house, using proprietary spice blends and steam kettles to reduce in-store labor. Next up is the rice, a deceptively simple but carefully controlled product. Chipotle's cilantro lime rice, white or brown, begins with high-grade long-grain rice sourced from domestic or South American suppliers. At the processing plant, the rice is rinsed to remove excess starch and then batch cooked in industrial steamers or pressure rice cookers. These machines are equipped with moisture and temperature sensors to maintain the exact texture and doneness that Chipotle requires. Fluffy, but not mushy, firm, but not undercooked. Once cooked, the rice is transferred to large mixing bowls where lime juice, chopped cilantro, and salt are added. Some facilities add a touch of oil for separation and sheen. Pneumatic arms or food-safe agitators mix the rice gently but thoroughly. From there, it is either packaged hot for immediate shipment or chilled using blast chillers, and packed cold for later reheating in-store. Salsas, like the mild tomato salsa, corn salsa, and spicy red chili version, are produced in facilities that combine both fresh vegetable processing and sauce manufacturing capabilities. Roma tomatoes, tomatillos, onions, and jalapenos are washed, diced, and de-seeded by high-speed dicers equipped with antimicrobial wash cycles. The chopped ingredients are portioned into blending tanks, where citrus juice, cilantro, salt, and spices are added. These tanks are chilled to preserve freshness during mixing. The salsas are filled into containers using multi-head fillers, which ensure precise weight and avoid overfilling. Each container is lidded, labeled, coded, and passed through X-ray or metal detection systems before being boxed and shipped under refrigeration. Because Chipotle prides itself on using fresh, preservative-free salsas, the cold chain must be rigorously maintained, and shelf life is generally short, often under 7 days. Guacamole is arguably one of Chipotle's most iconic items, and it, too, is partially factory-produced to reduce in-store prep time. Avocados are shipped to processing plants where they are ripened in ethylene-controlled ripening rooms. Once they reach optimal softness, they are halved, pitted, and scooped using semi-automated systems. Some facilities still rely on manual scooping to preserve texture and quality. The avocado pulp is then mixed with red onions, cilantro, lime juice, salt, and jalapenos in large mixing vessels outfitted with slow-speed paddle blades to avoid over-pureeing. The finished guacamole is portioned into food service containers and sealed under nitrogen-rich modified atmosphere packaging to prevent oxidation. These are chilled and shipped directly to stores, where they are used within a few days. Even toppings like shredded cheese and lettuce are processed off-site. Cheese blocks, such as Monterey Jack and white cheddar, in the massive production facilities where Reese's peanut butter cups are made, the process begins well before any chocolate is poured or any peanut butter is mixed. It starts with sourcing two critical ingredients: high-quality peanuts and specially formulated chocolate. The peanuts arrive at the plant in large, tightly sealed containers, having already undergone preliminary sorting at dedicated processing centers. However, the Reese's factory does not take any chances. Upon arrival, each shipment of peanuts is sampled and tested for aflatoxins, moisture content, and flavor quality. Only the best peanuts pass through to the next stage. The first critical transformation begins in the peanut roasting room, a cavernous area lined with continuous batch roasters. These machines look like giant horizontal drums that rotate slowly, while hot air circulates inside, ensuring each peanut is evenly toasted to bring out its natural oils and enhance flavor. Temperatures inside the roasters are tightly controlled, typically between 300 and 350 degrees Fahrenheit, and the roasting cycle can last anywhere from 10 to 30 minutes, depending on peanut size and desired roast level. Workers monitor color readings using optical sensors, making slight adjustments to the roast if necessary to achieve that signature Reese's flavor. Once roasted, the peanuts are transferred via conveyor belts to powerful cooling tunnels. Giant fans blow chilled, filtered air over the peanuts to halt the roasting process immediately, locking in the flavor profile. After cooling, the peanuts pass through a series of magnetic separators and vibrating screens to remove any foreign materials or remaining shell fragments, ensuring absolute purity. Next comes the grinding phase. The roasted peanuts are funneled into industrial grinders, massive machines equipped with heavy-duty steel plates that spin at high speeds. The first grind reduces the peanuts into a rough paste. Then a secondary, finer grind transforms the mixture into the silky, smooth peanut butter that will fill every cup. During grinding, small amounts of sugar, salt, and a plant-based emulsifier are added to stabilize the peanut butter and give it the slightly sweet, distinctly savory flavor that fans recognize instantly. The temperature is carefully managed during this phase, usually kept between 120 and 140 degrees Fahrenheit to ensure the oils remain stable and the texture remains creamy but not runny. The freshly made peanut butter is then pumped into enormous stainless steel holding tanks, where it is kept warm and agitated gently to maintain a consistent texture. These tanks are connected by sanitary piping to the production lines, allowing for seamless and hygienic movement of the peanut butter when it's time to fill the cups. Meanwhile, the chocolate preparation is already underway in a different section of the factory. Reese's uses a specially formulated milk chocolate blend that balances sweetness, cocoa flavor, and a creamy melt-in-the-mouth texture. Bulk chocolate arrives in the form of large solid blocks or liquid tanker shipments, depending on the factory's setup. If solid, the chocolate is first broken down in massive pre-melters, slowly heating it to around 110 degrees Fahrenheit to achieve a uniform, molten state. Once liquefied, the chocolate is pumped into tempering machines, sophisticated systems that cool and reheat the chocolate in a precise curve to stabilize the cocoa butter crystals. This tempering process is critical. It gives the finished cups their glossy appearance, firm snap, and excellent shelf stability. Now, with both chocolate and peanut butter ready, the cup assembly line begins. First, paper cup molds are automatically dispensed onto a continuously moving conveyor belt. High-speed chocolate depositor machines then squirt a carefully measured amount of molten chocolate into each paper cup, forming the base layer. The conveyor belt vibrates gently to help the chocolate settle evenly across the bottom and slightly up the sides of each mold. Immediately after this, the conveyor moves the cups through a cooling tunnel, where chilled air at around 50 degrees Fahrenheit partially solidifies the base chocolate layer. This quick cooling ensures that when the peanut butter is deposited, it won't sink all the way to the bottom of the cup, maintaining the ideal layered structure. Next, the creamy peanut butter is deposited into the center of each chocolate base using precision nozzles. The amount of peanut butter is meticulously controlled by programmable pumps, ensuring every Reese's cup has the same perfect peanut to chocolate ratio. Interestingly, the peanut butter filling itself is slightly cooler than the chocolate, typically around 80 to 90 degrees Fahrenheit, which helps it stay firm during the next stages of production. After the peanut butter is deposited, a second layer of molten chocolate is dispensed over the top, sealing in the peanut butter and forming the upper shell of the candy. Again, careful vibration of the conveyor ensures a smooth, even surface. At this point, visual inspection systems using high-speed cameras and AI algorithms scan the cups for consistency, checking fill levels, alignment, and any surface imperfections. Defective cups are automatically rejected from the line. The filled cups then pass through an extended cooling tunnel where they spend several minutes gradually chilling back down to around 45 degrees Fahrenheit. This staged cooling prevents the chocolate from blooming, a condition where cocoa butter rises to the surface and creates an unsightly white film. Instead, the cooling process locks in that deep, shiny chocolate sheen. Once fully cooled, the cups are ready for packaging. Automated robotic arms gently lift rows of finished Reese's cups and place them into pre-formed trays or directly onto flow wrapping machines. Each candy is enveloped in a thin, protective layer of branded orange packaging film. Heat sealers quickly fuse the edges of the wrapper shut, trapping a pocket of nitrogen gas inside. This inert atmosphere helps prevent oxidation, preserving freshness and flavor for extended shelf life. The wrapped candies are then grouped into multi-packs by high-speed cartoning machines, which fold and seal cardboard boxes around designated numbers of cups, whether it's a standard 2-pack, a king-size 4-pack, or a family-size bag of miniatures. These boxes are coded with manufacturing dates, lot numbers, and other traceability data before being stacked neatly onto pallets. Before the pallets leave the factory, a final quality control check is performed. Random packages are pulled from the line and subjected to a battery of tests, including weight checks, taste tests, visual inspections, and even X-ray analysis to ensure there are no contaminants or structural flaws inside the candies. Only when these samples pass inspection are the pallets shrink-wrapped and labeled for distribution. From there, the Reese's Cups embark on their journey through a highly coordinated supply chain. Pallets are loaded onto refrigerated trucks, kept at cool but not freezing temperatures to prevent the chocolate from melting or degrading. Distribution centers across the country receive the shipments, from which they are sent to grocery stores, convenience shops, vending machine suppliers, and even directly to online retailers. What's fascinating about the Reese's production process is how every detail, temperature, timing, movement, is optimized for both speed and quality. The factories are largely automated, with programmable logic controllers and centralized computer systems coordinating every phase, minimizing human error and maximizing consistency. Maintenance crews monitor the machinery continuously, ready to intervene if even the slightest deviation occurs. Yet, despite the heavy automation, a skilled team of chocolatiers, food scientists, and process engineers oversee operations daily, ensuring that the soul of the Reese's Cup, the perfect balance of creamy peanut butter and silky milk chocolate, is never compromised. In recent years, new technologies have further enhanced production. Advanced predictive maintenance uses AI algorithms to detect early signs of equipment wear, preventing costly downtime. Robotic packaging systems have become faster and more flexible, adapting to different product formats with minimal reprogramming. Even energy efficiency has improved dramatically, with modern factories recapturing waste heat from the roasting and tempering processes to reduce overall power consumption. The result of all this effort is what you hold in your hand, a Reese's Peanut Butter Cup with the same incredible taste that has delighted generations. From careful peanut selection to intricate chocolate tempering, from the first squirt of chocolate to the final seal of the wrapper, every step is a marvel of precision, engineering, and culinary artistry, ensuring that each bite delivers the unmistakable Reese's experience, time after time. The making of Hershey's milk chocolate begins long before any bars are molded or wrapped. It starts with sourcing one of the world's most essential commodities, cacao beans. Hershey's purchases massive quantities of cacao from regions like West Africa, Central and South America, and parts of Southeast Asia. Upon arrival at Hershey's specialized facilities, the cacao beans undergo strict quality control protocols. Sampling machines pull randomized beans from each shipment, checking for mold, contamination, fermentation quality, and flavor profiles. Only beans that meet Hershey's high standards proceed to production. The first major operation is cleaning. Beans travel through a series of shaking screens, magnetic separators, and powerful air jets that remove debris like sticks, stones, and dust. Once cleaned, the beans are routed to the roasting department. Here, colossal stainless steel drum roasters, each capable of handling thousands of pounds per batch, bring the beans up to roasting temperatures of around 250 to 300 degrees Fahrenheit. This roasting phase is crucial. It not only develops the rich cocoa flavors, but also loosens the shell from the nib, the part of the bean that will become chocolate. After roasting, the beans pass through cracking and winnowing machines. Heavy rollers crack the beans open, and powerful airflows then separate the lighter, papery shells from the heavier cocoa nibs. The nibs are collected and sent immediately into the refining phase. The shells, interestingly, don't go to waste. Many are repurposed as agricultural mulch or used in animal feed. The next transformation happens in the grinding rooms. Industrial grinders crush the nibs into a thick, gritty paste known as chocolate liquor. Despite its name, it contains no alcohol. Giant stone mills or modern ball mills spin tirelessly, reducing particle sizes to less than 100 microns. This grinding process releases the cocoa butter within the nibs. turning the dry nibs into a fluid, rich mass. At this stage, the chocolate liquor is either stored or immediately processed depending on the specific recipe being produced. For Hershey's signature milk chocolate, chocolate liquor alone is not enough. It must be blended with several other ingredients: sugar, milk, and cocoa butter, among others. Hershey's famously uses fresh condensed milk rather than powdered milk, a technique that imparts its distinctive flavor. Tankers bring in condensed milk that has already been pasteurized and quality tested for microbial safety. The milk is combined with sugar in large stainless steel kettles and cooked to form what is known as a milk crumb, a dry, sweet, caramelized powder that becomes the base for Hershey's milk chocolate. The milk crumb, chocolate liquor, and additional cocoa butter are blended together in massive mixers that resemble horizontal cement mixers but are built for food-grade standards. In these tumbling vessels, the blend of ingredients becomes a coarse chocolate dough. This dough is then fed through refining rollers, 5 or 6 massive polished steel rollers stacked horizontally. As the dough passes through each successive roller gap, it is compressed and sheared finer and finer, reducing the sugar and cocoa particles to just the right microscopic size to ensure a smooth texture. At this point, the chocolate still lacks the silky consistency and full flavor that people expect. That's where one of the most crucial steps in chocolate making enters: conching. Hershey's uses giant conching machines, massive, heavy-duty mixers with granite rollers that agitate, aerate, and warm the chocolate dough for hours. Traditional conching could take up to 72 hours, but with modern methods and specialized Hershey's technology, the time has been optimized without sacrificing quality. During conching, volatile acids and bitter flavors evaporate away, while cocoa and milk flavors mellow and deepen. At the same time, the continuous mixing further reduces any remaining coarse particles and disperses the cocoa butter thoroughly throughout the mass. Temperature control during conching is critical. The chocolate must stay within an exact range, typically between 130 to 180 degrees Fahrenheit, depending on the desired flavor development. Ventilation hoods draw off unwanted volatiles, and sensors embedded throughout the conches constantly report data back to automated control systems, adjusting speed and temperature as needed. Following conching, the chocolate moves into the tempering phase. Tempering is an art and science all its own. Chocolate is carefully cooled and reheated through specific temperature curves to create stable cocoa butter crystals. This gives finished chocolate its snap, gloss, and resistance to melting at room temperature. Hershey's uses continuous tempering machines, which can process thousands of pounds per hour. These machines use a series of heated and cooled zones to guide the chocolate through its crystal formation journey with pinpoint accuracy. Improper tempering would result in chocolate that's dull, crumbly, or prone to blooming, a white discoloration, so this step must be executed flawlessly. Once tempered, the liquid chocolate is transported through heated pipes to the molding stations. There, automated depositors squirt precise amounts of chocolate into endless arrays of molds, some shaped for classic Hershey's bars, others for miniature versions or seasonal specialties. The molds vibrate rapidly on oscillating tables to eliminate any air bubbles and ensure an even surface. The molds then enter a long cooling tunnel, a carefully calibrated environment where the chocolate solidifies slowly and evenly. Inside the tunnel, the temperature drops gradually from around 70 degrees Fahrenheit to about 50 degrees, preventing thermal shock and ensuring that the chocolate sets with a fine, smooth crystal structure. After cooling, the solid chocolate is demolded. High-speed mechanical arms flip and flex the molds, gently releasing the perfectly formed bars onto conveyor belts. At this stage, visual inspection systems equipped with high-speed cameras and AI check every piece for uniformity, detecting even minor surface defects or molding errors. Imperfect chocolates are removed from the line for recycling back into the production process. The next step is packaging. For Hershey's bars, the chocolate rides conveyors into flow wrapping machines. Each bar is enveloped in a tight sleeve of foil and then an outer branded paper wrapper. Modern flow wrappers work at astonishing speeds, often wrapping hundreds of bars per minute with perfect precision. The wrapped bars are coded with expiration dates, batch numbers, and tracking information to ensure full traceability from production through to sale. Once wrapped, the bars are collated into cartons or retail trays by robotic packers, which arrange them neatly in boxes that are then sealed, labeled, and stacked onto pallets. Before shipment, a random sample from every production batch undergoes additional quality assurance tests, including break tests, melt tests, taste panels, and microbial analysis. Only after passing all these checks are the pallets released for distribution. The finished Hershey's milk chocolate bars then enter the logistics phase, moving through regional distribution centers that coordinate delivery to supermarkets, convenience stores, cinemas, and countless other retailers around the world. Throughout the distribution chain, temperature control remains critical. Warehouses and trucks are climate controlled to prevent the bars from experiencing temperature swings that could cause chocolate bloom or textural changes. Throughout the entire factory process, Hershey's leverages advanced automation, continuous monitoring, and decades of chocolate-making expertise to ensure that every bar tastes as iconic and consistent as the last. The level of control is extraordinary. Chocolate viscosity, particle size distribution, moisture levels, and flavor profiles are measured and adjusted in real time using sophisticated inline sensors and laboratory tests. In recent years, Hershey's has also invested heavily in sustainability, working directly with cocoa farmers through its Cocoa for Good program to promote ethical sourcing, better farming practices, and environmental stewardship. This commitment ensures not just the continued availability of high-quality cacao, but also a better future for the communities that produce it. The journey of a Kit Kat begins with two major components: the chocolate coating and the crisp wafer core. Both are manufactured separately and in parallel streams before being married together into the unmistakable Kit Kat form. Each ingredient, each layer, and each step is engineered with astonishing precision to create the perfect snap, crunch, and creamy finish that Kit Kat is famous for. The process starts with the preparation of the chocolate. Kit Kat's signature coating is slightly different from pure chocolate. It is technically a compound chocolate, specially formulated to give a smooth melt and quick setting properties ideal for enrobing wafers. At factories like Nestlé's York facility in the UK or similar plants worldwide, bulk cocoa liquor, cocoa butter, sugar, and milk solids are combined. The cocoa beans that form the basis of the liquor are sourced from sustainable suppliers, cleaned, roasted, and ground into fine paste months before production even begins. To prepare the chocolate coating, the cocoa liquor is blended with sugar and powdered milk in enormous stainless steel mixers. This mixture is then refined through a series of precision-calibrated rollers, reducing the particle size to around 20 microns, finer than the human tongue can detect. The refining phase is essential to create the smooth mouthfeel Kit Kat lovers expect. Following refinement, the chocolate mass moves into conching machines, where it is slowly mixed, aerated, and heated. This removes any bitter flavors and unwanted acidity, while promoting the development of a creamy, caramel-like flavor that defines Kit Kat's chocolate. Temperature control during conching is rigorously maintained at around 135 to 180 degrees Fahrenheit, depending on the recipe. Once the chocolate reaches the right flavor and viscosity, it is moved into tempering units, where it's carefully cooled and reheated to produce stable cocoa butter crystals. Proper tempering ensures that the finished chocolate will have a shiny appearance, a satisfying snap, and resistance to blooming. Meanwhile, in another section of the factory, the production of the wafer sheets is underway. Wafer batter, made from a simple mixture of wheat flour, sugar, vegetable oil, leavening agents, and water, is mixed in giant, computer-controlled vats. The batter is pumped through piping systems directly to high-speed wafer baking ovens, each stretching tens of meters in length. These wafer ovens consist of two continuously moving steel belts that sandwich the batter and pass through a baking tunnel. As the belts travel, radiant heat, conduction, and convection work together to bake the batter into ultra-thin, crisp wafer sheets. Each sheet emerges from the oven perfectly cooked, around 2 to 3 millimeters thick, with a delicate, light texture and a uniform golden brown color. After baking, the wafer sheets are rapidly cooled using forced chilled air to prevent moisture absorption. They are stacked and transported via conveyor belts to the cream spreading stations. Here, a thin layer of specially formulated filling, a mixture typically based on ground wafer crumbs, vegetable fats, sugar, and milk solids, is evenly spread across the wafers. The filling not only enhances the flavor, but also acts as a structural adhesive, bonding the multiple wafer layers together. Usually, 3 or 4 wafer sheets are stacked, with cream filling between each layer. These multi-layered blocks are then pressed under controlled pressure to ensure perfect bonding without cracking or crushing the delicate wafers. After resting for stabilization, the wafer blocks are transferred to high-speed cutting machines. The cutting process is a masterpiece of mechanical precision. Using laser guides and ultrasonic blades, the blocks are sliced first longitudinally, then crosswise into the familiar slim Kit Kat finger dimensions. Every cut must be perfect. Any deformation could later disrupt the enrobing process or spoil the iconic snap experience. Once cut, the wafer fingers are ready for enrobing. Conveyors carry them through a chocolate waterfall inside the enrobing machines. A curtain of tempered Kit Kat chocolate cascades over the wafers, completely coating them on all sides. Excess chocolate is blown off the bottom with controlled air jets, creating the thin chocolate layer underneath that gives Kit Kat its balanced chocolate to wafer ratio. Directly after enrobing, the fingers pass through a vibrating section of the conveyor to settle the chocolate coating and eliminate air bubbles. They then enter a series of cooling tunnels where cold, dry air, typically kept between 40 and 50 degrees Fahrenheit, slowly solidifies the chocolate coating without causing condensation, which would ruin the texture. At this point, the individual fingers are grouped together. Kit Kat is traditionally made with 4 fingers to a bar, although mini versions, single fingers, and chunkier variants are also produced. Robotic arms align and group the fingers with exact spacing between them before feeding them into wrapping machines. Kit Kat's iconic red and white wrapper is a masterpiece of branding and practical design. Wrapping is done using ultra-fast flow wrappers that synchronize perfectly with the grouping conveyors. Each set of fingers is enveloped in foil or a plastic laminate film, which protects against moisture and oxygen while maintaining the crunch of the wafer and the smoothness of the chocolate. The wrapping machines heat seal the edges at high speed, and rollers gently press and fold the sealed packs for that crisp, tight package finish Kit Kat is known for. As the wrapped bars move down the line, high-speed scanners and cameras inspect each package for correct seal integrity, label placement, and print clarity. Imperfections are detected in milliseconds, and defective packs are automatically ejected into collection bins for recycling. Once the Kit Kats are individually wrapped, the next stage is boxing and palletizing. Robotic case packers arrange the wrapped bars into boxes or display cartons, which are then sealed with automatic tapers and labeled with tracking information. Each box is carefully weighed and scanned to ensure it matches target specifications before being stacked onto pallets by robotic arms or palletizing machines. Throughout the entire production process, rigorous quality control is applied at every major step. Samples of chocolate, wafer batter, finished wafers, and completed bars are pooled at regular intervals for lab analysis. These tests include moisture content checks, microbiological safety testing, taste panels, and break strength tests to ensure the classic crisp break of a Kit Kat remains perfect batch after batch. In addition to inline testing, larger batch samples are subjected to accelerated aging studies to simulate how the product will perform over its shelf life. Sensory evaluation booths, staffed by trained taste testers, ensure that every batch maintains the exact flavor, aroma, texture, and mouthfeel that consumers expect. Once the Kit Kats are boxed and palletized, they are shipped out from climate-controlled distribution centers. Transport conditions are carefully managed to prevent temperature fluctuations that could cause chocolate bloom or wafer softening. Many shipments are refrigerated during summer months or in hotter climates to guarantee the product arrives in prime condition. Kit Kat's industrial production is a brilliant choreography of automation, sensory science, and quality management. Despite the high level of automation, human oversight remains crucial. Line operators monitor critical control points, adjust machine settings, respond to alarms, and carry out maintenance to keep the lines running smoothly, often 24 hours a day, 7 days a week. Recent advancements have further refined the process. State-of-the-art production lines now incorporate AI-driven predictive maintenance, allowing engineers to anticipate mechanical failures before they happen. Machine learning algorithms also optimize ingredient mixing, cooking times, and cooling profiles, subtly adjusting for real-time variables like humidity, ingredient lot variation, or slight temperature shifts in the facility. Kit Kat's commitment to sustainability is woven into production as well. Modern factories are equipped with energy recovery systems that reuse heat from the ovens and chillers. Water used in cooling and cleaning processes is recycled wherever possible. Additionally, Kit Kat's cocoa is 100% sourced through programs like Rainforest Alliance certified farms, ensuring ethical and environmentally responsible cocoa farming practices. Each Kit Kat bar that makes it into a consumer's hands is the end product of thousands of micro decisions and perfectly tuned processes: baking, layering, cutting, coating, cooling, wrapping, all executed with a level of precision that would make a Swiss watchmaker proud. The crisp snap of the break, the lightness of the wafer, the creamy melt of the chocolate, every detail is the result of decades of research, refinement, and relentless pursuit of chocolate and wafer perfection. It all begins with the chicken itself, fresh, never frozen, and selected according to strict specifications that have been standardized over decades. At the heart of KFC's fried chicken production is consistency, and that starts with sourcing poultry from highly regulated farms, often contracted directly to supply birds that meet stringent criteria for weight, size, age, and health. These chickens are typically raised under controlled conditions, with monitored feeding schedules and veterinary oversight, ensuring uniformity in muscle development and fat content. Farmers work closely with the suppliers to deliver birds that fall within the optimal range for processing, which generally hovers around 4 to 6 pounds per whole bird, depending on the regional market. Once the birds arrive at the poultry processing plant, they undergo a sequence of highly regulated steps designed to transform them into the individual cuts used in KFC's iconic fried chicken buckets. The first step is stunning and slaughter, where automated systems humanely render the birds unconscious before they are swiftly slaughtered. This is followed by scalding, immersing the carcasses in warm water to loosen feathers, and defeathering using a mechanical plucking system that employs rotating rubber fingers to strip feathers from the skin without damaging the flesh. The next phase involves evisceration, where internal organs are removed through a series of automated mechanical arms and cutting systems. Inspectors, both human and digital, examine the internal cavities for any signs of disease or contamination. The birds are then washed thoroughly in a series of chilled water baths and antimicrobial sprays to reduce surface bacteria. After this, the carcasses are chilled rapidly, often through immersion in ice water or air chilling tunnels, to bring the internal temperature down to safe levels before further processing. With the whole birds chilled and inspected, they are transferred to the cutting line. This is where the chicken is portioned into the familiar cuts used in KFC recipes: drumsticks, thighs, breasts, wings, and occasionally rib portions, depending on the market. High-speed blades and vision-guided robotic systems ensure that each piece is cut uniformly. Some facilities even use X-ray and laser-guided cutting to detect bone structure and fat lines, optimizing yield and reducing waste. The chicken pieces are then sorted by size and weight, ensuring every batch has a consistent mix for packaging and preparation. After cutting, the chicken is placed into sanitized plastic totes or stainless steel trays and sent to the marination area. This is a crucial step that lays the foundation for KFC's signature flavor. The original recipe chicken is soaked in a wet brine that typically includes water, salt, and phosphate-based tenderizers to enhance juiciness and flavor retention. The chicken is placed into large tumblers, rotating drums with paddles inside that gently agitate the meat to ensure thorough penetration of the brine. This marination process typically lasts for a fixed duration, anywhere from 30 minutes to several hours, depending on the specific product line. But marination is just the beginning. What truly sets KFC apart is the breading process, a meticulously controlled step where secrecy and technique intertwine. The chicken is removed from the brine and allowed to drain slightly before being transferred to the breading stations. The breading mixture, known for its secret blend of 11 herbs and spices, is kept under strict control. At the manufacturing level, this seasoning is produced in centralized spice blending facilities, measured with pharmaceutical-level precision, and shipped to stores or distribution centers in tamper-proof bags. Operators follow a carefully choreographed breading procedure known as the 7-to-10-7 method. First, the chicken is placed into a flat metal pan with the dry breading mix and hand-tossed 7 times in a specific pattern to ensure an even coating. Then the pieces are compressed down into the breading mixture for 10 seconds. This step helps the coating adhere and creates the famous textured crust. Finally, the pieces are shaken 7 more times and arranged neatly onto perforated trays for the next stage. This manual method, despite being labor-intensive, is a cornerstone of KFC's identity and helps achieve the distinctive craggy exterior that customers recognize instantly. Once breaded, the chicken is moved to the fryers. KFC uses high-capacity pressure fryers, commercial machines that resemble deep fryers, but with tightly sealed lids that allow cooking under pressure. This equipment is critical for achieving the brand's signature texture: crispy on the outside, juicy on the inside. The sealed environment traps steam from the chicken's internal moisture, cooking it rapidly while locking in juices. The breaded pieces are loaded into metal baskets, which are then placed into the preheated pressure fryers filled with proprietary frying oil blends, typically high in stability and low in trans fats. Each fryer is pre-programmed to precise cooking parameters, controlling temperature and time based on the chicken type: bone-in, boneless, tenders, or wings. For original recipe bone-in chicken, the typical cooking cycle runs around 10 to 15 minutes at roughly 325 degrees under pressure. As the pressure builds, the internal temperature of the chicken rises quickly, reducing cook time while preserving moisture. Throughout the cooking process, sensors inside the fryer monitor oil temperature, pressure levels, and cooking duration, ensuring every batch turns out uniform and safe to eat. Once cooking is complete, the fry baskets are lifted automatically or by hand, and the chicken is allowed to drain for a brief period over the oil vat. Operators then transfer the finished product to a holding station, typically a heated cabinet or a moisture-controlled drawer that maintains the chicken at a safe temperature, usually above 140 degrees F, while preventing the crust from getting soggy. These holding cabinets are set to timers that ensure chicken is only kept for a limited time before it is discarded or rotated out, reinforcing KFC's strict freshness policy. Throughout this entire process, food safety is paramount. Every station is equipped with hand-washing sinks, sanitizer dispensers, and cleaning schedules that are enforced hourly. Employees wear gloves, aprons, and hairnets or caps, and facilities conduct routine microbial testing on surfaces and air to minimize contamination risks. Temperature logs, batch records, and fryer oil quality checks are performed regularly. The oil itself is filtered several times per day using built-in filtration systems that remove particulates and extend the oil's usable life while maintaining flavor quality. But the process doesn't begin or end in the kitchen. At the supply chain level, KFC relies on a cold chain network that keeps the chicken and ingredients at safe temperatures from the processing plant to the store. After the chicken is marinated and portioned at regional facilities, it is vacuum sealed or packed into airtight food-grade plastic bags, then stored in refrigerated trucks with active temperature tracking systems. GPS-enabled trailers ensure the logistics team can monitor both temperature and location in real time, avoiding spoilage or delays. The spice blends, breading flour, oil blends, and packaging materials are all shipped through similarly optimized networks, allowing stores to receive fresh inventory on a scheduled basis without interruption. When the chicken finally reaches the individual KFC restaurants, it is stored in walk-in coolers, prepped according to the exact procedures laid out by corporate training, and cooked fresh on-site throughout the day in small batches to keep up with demand. The entire system is designed for scalability and control. From a small store in a rural town to a flagship location in a major metropolis, the chicken tastes almost identical. That's the power of systematized food production at scale. Interestingly, much of KFC's fried chicken production still retains a manual, human-guided feel despite the high-tech systems that support it. While robotics and automation are increasingly common in many fast food chains, KFC's breading process continues to rely heavily on trained workers. This combination of human skill and industrial precision contributes to the unique texture and flavor of the final product. It all begins with the raw materials. At the core of the Big Mac are its two beef patties, 100% pure ground beef with no fillers, additives, or preservatives. These patties are made from specially selected cuts of beef, typically chuck, round, and sirloin, all blended to achieve McDonald's-specific fat-to-lean ratio, usually around 80-20. The cattle are sourced from approved ranches and farms, where animal welfare, feed quality, and traceability are tightly controlled. These suppliers operate under strict auditing and food safety programs to ensure consistency and safety throughout the entire supply chain. At the beef processing plants, the meat is first received in chilled form and stored in temperature-controlled environments. It then moves to large-scale grinders where the cuts are ground to a uniform consistency. The grinding process uses precision-engineered machinery that not only ensures even texture, but also mixes the fat content evenly throughout the meat. After grinding, the meat is portioned into exact patty sizes using high-speed forming equipment. Each Big Mac patty is a 1.6-ounce round that measures precisely to fit the 3-part sesame seed bun. Once the patties are formed, they are immediately flash frozen using cryogenic tunnels or spiral freezers. This locks in moisture and prevents microbial growth while maintaining the structural integrity of the patty. The frozen patties are then stacked into cartons, sealed, and loaded into refrigerated trucks that maintain a cold chain at all times. They are shipped to McDonald's distribution centers, which in turn supply local restaurants with scheduled deliveries to ensure freshness and efficient inventory management. But a Big Mac isn't just beef. Another critical component is the famous 3-part sesame seed bun: the crown, the club, and the heel. These buns are produced in large-scale commercial bakeries that specialize in McDonald's specifications. The dough is made from wheat flour, water, yeast, sugar, and conditioners to ensure softness and volume. The mixing and proofing process is closely monitored by computerized systems that control dough temperature and humidity. Once proofed, the dough is portioned into perfectly sized balls and dropped into custom baking molds designed specifically for the Big Mac's three-part structure. The top bun is topped with sesame seeds just before baking. Conveyor ovens bake the buns at precisely calibrated temperatures for consistent color, texture, and internal moisture. After baking, buns are cooled on spiral cooling racks, then sliced, and the three segments are separated and packaged accordingly. Like the patties, the buns are then flash frozen or refrigerated and shipped to McDonald's outlets. Another defining component of the Big Mac is its sauces and toppings, specifically the Big Mac Special Sauce. The exact formula is proprietary, but the flavor is unmistakable. A tangy, creamy, slightly sweet sauce that combines elements of mayonnaise, mustard, relish, garlic, onion powder, and other spices. This sauce is manufactured in centralized condiment processing facilities, where ingredients are blended in large stainless steel tanks using industrial mixers that maintain a homogeneous emulsion. The final product is pumped into sealed, portion-controlled containers that are shipped cold to restaurants. In addition to the sauce, there are sliced pickles, dehydrated onions that are rehydrated on-site, shredded iceberg lettuce, and American cheese. The pickles are cut from whole cucumbers and brined in tanks with a proprietary vinegar and spice solution. They're sliced to a uniform thickness, then packed in brine to retain crunch and flavor. The onions come pre-chopped and dehydrated to extend shelf life and reduce spoilage. They are soaked in cold water at the store level before use. Lettuce is shredded in controlled processing plants and packed into vacuum-sealed bags. It must meet specific dimensions for length and width to ensure even coverage and manageable volume in the sandwich. The cheese, a processed slice tailored for meltability and flavor stability, is individually wrapped and delivered refrigerated. At the restaurant level, the Big Mac is assembled in a precise, time-tested sequence designed for speed and uniformity. When a customer places an order, the kitchen system relays it to the grill and assembly line. The patties are cooked on a dual-sided clamshell grill, a piece of kitchen equipment that cooks both sides of the patty simultaneously. This reduces cook time to less than a minute while ensuring the internal temperature reaches the USDA required safe zone of 155 degrees Fahrenheit or higher. The grills are calibrated multiple times a day to maintain consistent heat, and they include timers and temperature sensors that alert the crew when patties are done. Simultaneously, the buns are toasted on a vertical conveyor toaster that crisps the inside surfaces while leaving the exterior soft. Each bun, top, middle, and bottom, is inserted into a specific slot in the toaster, ensuring that they emerge in the correct sequence for stacking. The bun toaster is also calibrated for toast color and surface temperature, both of which affect the texture and structural integrity of the final sandwich. Once the patties and buns are ready, the assembly begins on a stainless steel prep table or station called the sandwich build line. Each component is added in exact order. The heel receives a half teaspoon of rehydrated onions, followed by shredded lettuce, one slice of cheese, and the first cooked beef patty. The middle bun is then placed on top, followed by a second layer of sauce, onions, lettuce, and pickles, then the second patty. Finally, the top bun is placed to crown the entire structure. Employees are trained to assemble the Big Mac with a high degree of consistency, using scoops and dispensers designed to deliver precise amounts of sauce, lettuce, and onions. Visual guides are often posted above the station, and training involves repetition to internalize the build order and portion sizes. Speed is crucial, but accuracy takes priority. Each Big Mac must be indistinguishable from the next. Once assembled, the sandwich is wrapped in specially designed cardboard clamshells or wrappers that help maintain heat without causing sogginess. These are placed in warming areas or immediately bagged for customer pickup, depending on the workflow of the kitchen. Each Big Mac is usually served within a 5 to 10 minute window of cooking, ensuring it is hot, fresh, and true to form. Food safety and quality assurance are embedded in every stage of this process. The patties are temperature checked with digital thermometers. Sauce containers are labeled with use by times. Lettuce and onions are discarded after a certain number of hours out of refrigeration. Crew members follow strict hygiene protocols, including hand washing every hour, wearing gloves, and rotating utensils to prevent cross-contamination. Regular audits and surprise inspections ensure compliance with these standards. McDonald's kitchens also operate with a high level of automation and integration. Point-of-sale systems are linked to kitchen monitors, which display order sequences in real time. Inventory systems track ingredient usage and automatically flag restocking needs. Even the toaster and grill equipment is connected to central management systems that log performance data, usage cycles, and maintenance schedules. Behind the scenes, logistics play a crucial role in Big Mac production. From farm to fryer, the ingredients move through a vast cold chain network supported by regional distribution centers. These hubs maintain constant temperature control and manage stock rotation to ensure that every restaurant has fresh, usable inventory. McDonald's works closely with third-party logistics companies and in-house supply teams to coordinate deliveries across thousands of outlets every day. Even sustainability is being integrated into the Big Mac's life cycle. McDonald's has committed to sourcing beef more responsibly, using packaging materials that are recyclable or compostable, and reducing waste in the supply chain. Many of the buns are baked in facilities that run on renewable energy, and fryers now use low-emission heating systems. The lettuce and pickles are sourced from farms that practice water conservation and integrated pest management. In the end, the Big Mac is more than a sandwich. It's a manifestation of precision food engineering on a global scale. What might seem like a simple fast food item is the result of decades of refinement in agriculture, logistics, processing, and food safety. The carefully orchestrated choreography of farmers, food scientists, line cooks, and engineers ensures that every customer experiences the same taste, texture, and satisfaction with every bite. Whether it's the sizzle of the patties on the grill or the final crown of the sesame bun, every step is designed to deliver that unmistakable Big Mac experience. It all starts with the dough. Domino's dough is made in regional commissaries, large-scale production facilities that supply fresh dough to stores several times a week. These commissaries receive shipments of high-quality wheat flour from trusted grain suppliers. The flour, typically enriched and with a mid-range protein content around 12%, is combined with water, yeast, salt, sugar, and a small amount of oil in massive stainless steel mixers. These mixers, with capacities ranging from hundreds to thousands of pounds, mix the dough until it reaches the desired elasticity and gluten development. The dough is then allowed to rest and rise in temperature and humidity-controlled proofing rooms. These chambers regulate fermentation precisely, letting the yeast activate and produce carbon dioxide, which is what gives the dough its airy structure. This stage is not rushed. Domino's prioritizes flavor and texture, allowing the dough to ferment for several hours or even overnight to develop deeper taste and a balanced chew. After proofing, the dough is portioned into individual balls using industrial dough dividers and rounders. Each ball is scaled for the correct pizza size: small, medium, large, or extra large, and placed into trays lightly coated with cornmeal or oil to prevent sticking. These trays are stacked into rolling racks and moved into refrigerated holding rooms. Chilled to slow further fermentation, the dough balls are now ready for transport. They're boxed, loaded into cold chain delivery trucks, and shipped to Domino's outlets across the region on a tightly managed delivery schedule. Now comes the tomato sauce, an essential component that gives every pepperoni pizza its acidic punch and signature flavor base. The sauce is made at centralized processing plants using vine-ripened tomatoes, typically harvested at peak season and steam-peeled for optimal flavor preservation. The tomatoes are ground and mixed with a proprietary blend of spices, including oregano, basil, garlic powder, onion powder, salt, and sometimes a pinch of sugar to balance acidity. This sauce is then pasteurized to ensure shelf stability and safety, and filled into sealed plastic pouches or buckets, which are shipped refrigerated to each Domino's location. Cheese, too, is a cornerstone ingredient in every pepperoni pizza. Domino's uses a special low-moisture, part-skim mozzarella blend developed for optimal melt, stretch, and browning. Large cheese manufacturing plants shred or dice the mozzarella into uniform pieces that fall easily onto the pizza and melt consistently. The cheese is bagged, nitrogen flushed to prevent spoilage, and stored cold until it's needed. Domino's has strict cheese specifications that regulate fat content, meltability, and even browning color curves during baking. And of course, there's the pepperoni. Domino's pepperoni is a type of cured, spiced sausage made from a mix of beef and pork. The meat is ground and blended with a spice mixture that includes paprika, garlic, crushed red pepper, fennel seed, and curing salts. After being emulsified, the mixture is stuffed into collagen casings and fermented to develop its tangy flavor profile. The pepperoni is then slow-dried, sometimes smoked, and aged until it reaches the correct firmness. Once matured, it's sliced into perfect, thin rounds that crisp slightly when baked but retain their juicy center. These slices are packed into refrigerated cases, typically with a layer of wax paper to prevent sticking, and distributed to stores for daily use. At the store level, the pizza making process begins when an order is received, either online, via app, or in-store. The store crew retrieves a dough ball from the walk-in cooler and places it on a prep table dusted with cornmeal or flour. Unlike hand-tossed pizzerias, Domino's uses a combination of manual and mechanical techniques to stretch dough. The dough ball is pressed using a dough press or roller to achieve the correct size and thickness. Then it may be hand-finished to achieve an even round shape with a defined edge, or cornicione. Once the crust is prepared, the pizza moves down the make line. A ladle of tomato sauce is spread in a spiral motion from the center outward, leaving a consistent border around the edge. Precision here is key. Too much sauce and the crust gets soggy. Too little and the pizza lacks flavor. Domino's uses portion-controlled utensils to ensure uniform application across thousands of pizzas a day. Next comes the cheese. Employees grab pre-measured amounts of shredded mozzarella from cold bins and scatter it evenly over the sauced crust, making sure to reach the edges to maximize melt and appearance. The cheese-to-sauce ratio is carefully designed to complement the crust thickness and baking conditions in the oven. Domino's often uses cheese guides or weight scales to prevent under or over application. Then it's time for the pepperoni, the star of the show. Domino's applies pepperoni in a uniform pattern, usually a ring-based layout that ensures each slice of the final pizza gets equal coverage. The pepperoni is placed on top of the cheese, so it crisps and curls slightly during baking, creating those little greasy, flavorful cups that have become a hallmark of American pepperoni pizza. The number of pepperoni slices is not left to chance. Domino's has precise count targets per size, such as 30 slices for a medium and 40 for a large, ensuring every customer receives the expected experience. Once built, the raw pizza is placed onto a pizza screen or baking tray and sent into a conveyor oven. Domino's signature baking method. These ovens, called impinger ovens, are long, tunnel-like machines that use jets of superheated air to cook the pizza quickly and evenly. The oven belt moves at a fixed speed, typically cooking a pizza in about 6 to 7 minutes at a temperature of approximately 465 degrees Celsius to 500 degrees. The impingement cooking method forces hot air onto the top and bottom surfaces of the pizza simultaneously, ensuring a crisp crust and melted, browned cheese with consistent results. As the pizza exits the oven, crew members perform a quick visual check for doneness. The cheese should be fully melted and bubbling, the pepperoni slightly curled with crispy edges, and the crust golden brown. The baked pizza is transferred to a cutting board and sliced with a rolling blade into even segments, typically 8 for a large pizza. The blade is wiped between uses to prevent sauce and cheese buildup. The pizza is then placed into a specially designed Domino's pizza box made from recycled corrugated cardboard. These boxes are ventilated to allow excess steam to escape, preventing sogginess during delivery. Each box is folded and branded with Domino's blue and red logo and has space for order stickers, promotional labels, and QR codes. A thermal lining or pizza insert may also be used in some regions to help retain heat during transport. Once boxed, the pizza is either handed over to a customer in-store or placed into an insulated delivery bag. These bags are engineered to retain heat and allow limited airflow, keeping the pizza hot but not steamy. Domino's delivery drivers follow optimized GPS routes generated by proprietary software that prioritizes speed and traffic conditions. Many stores use heat racks or warming stations to hold pizzas briefly while waiting for drivers or curbside pickup. Behind the scenes, Domino's uses sophisticated technology to monitor every step. The point-of-sale system automatically tracks inventory levels. Real-time analytics inform store managers about the number of pizzas being ordered, the time each step takes, and potential bottlenecks. Domino's Pizza Tracker gives customers live updates on the progress of their order, from prep to baking to out for delivery, driven by timestamps and kitchen inputs. Cleanliness and food safety are integral to every stage. Dough trays and utensils are washed in commercial dish machines between uses. Gloves are worn and changed frequently. Prep stations are sanitized regularly throughout the day. All cold ingredients are stored in reach-in coolers with thermometers to maintain optimal temperature. Internal audits and third-party inspections ensure compliance with food safety standards and corporate procedures. The production of Starbucks products, particularly its packaged coffee offerings that end up in grocery stores, retail outlets, and international supply chains, begins long before a single bean is roasted. The entire process is built on one foundational element: green coffee sourcing. Starbucks, known for its commitment to quality and consistency, manages one of the most tightly controlled and globalized green coffee sourcing operations in the food and beverage industry. This first phase, the pre-roasting segment, is where the company sets the tone for every cup of coffee or bottled product it will eventually serve. And it's here we begin our highly detailed step-by-step journey. The green coffee sourcing process starts at origin in the tropical coffee-growing regions that straddle the equator, primarily Latin America, East Africa, and Southeast Asia. Starbucks primarily uses Arabica beans due to their more nuanced flavor profiles compared to the hardier but less complex Robusta variety. Within the Arabica family, beans are selected based on elevation, soil composition, rainfall, and harvest timing. Starbucks maintains long-standing relationships with coffee growers, cooperatives, and export mills in countries like Colombia, Ethiopia, Guatemala, Indonesia, Brazil, and Rwanda. But it's not as simple as ordering beans in bulk and having them shipped. Starbucks uses a proprietary set of sourcing standards known as Coffee and Farmer Equity Practices. These standards are not only a requirement for suppliers to be eligible, but also a multi-layered auditing framework. CAFE practices address 4 critical areas: product quality, social responsibility, environmental leadership, and economic transparency. Every farm or co-op that sells beans to Starbucks must pass rigorous inspections in these categories, many of which are carried out by third-party auditors trained in agricultural and labor practices. Once a farm or producer is approved under CAFE practices, the beans are harvested, typically by hand. Hand picking ensures that only ripe coffee cherries are selected, an essential factor in achieving flavor consistency in the final roast. These cherries are then processed at or near the farm using either the washed method. The washed method involves removing the pulp and fermenting the beans to eliminate the mucilage before drying, producing a cleaner, brighter flavor. The natural method dries the entire cherry and imparts a fruitier, heavier profile. The method used depends on the country, the farmer's infrastructure, and the target flavor profile desired by Starbucks blending teams. Once processed, the green beans are dried to a specific moisture content, usually between 10% and 12%, and stored in parchment until they are ready for export. Before leaving the origin country, the beans undergo a final hulling process to remove the parchment layer. At this stage, Starbucks' quality assurance teams at origin perform multiple assessments. These include physical evaluations and cupping, an industry standard tasting method. Starbucks QA cuppers evaluate the green coffee on attributes like acidity, body, balance, sweetness, and aftertaste. Only those lots that meet Starbucks' sensory and structural requirements are approved for shipment. Approved beans are then packed into multi-layered jute bags with protective liners or into GrainPro plastic bags that guard against moisture and pests during transit. Each bag is tagged with a traceable barcode or lot number, which connects it to a digital database. This data includes not just the country and region of origin, but the exact farm or cooperative, harvest date, processing method, and quality score. This traceability is critical, not just for transparency and accountability, but also for quality replication year after year. Now begins the logistics phase. Starbucks contracts with specialized freight companies that understand the requirements of green coffee shipping. These beans are incredibly sensitive to temperature and humidity, even in raw form. A single exposure to high heat or excess moisture during transit can cause mold growth or flavor degradation. The beans are typically transported in temperature-stabilized shipping containers. If traveling by sea, the containers are outfitted with humidity control packs and dehumidifying systems. If air freight is used, the bags are carefully palletized, shrink-wrapped, and tagged with sensors that monitor environmental conditions throughout the journey. Upon arrival at one of Starbucks' roasting and manufacturing facilities, such as those located in York, Pennsylvania, Augusta, Georgia, Sandy Run, South Carolina, or Amsterdam, Netherlands, the green beans are unloaded, inspected, and entered into the factory's inventory management system. Before any production begins, each new shipment undergoes additional quality control. Samples from each bag or container are pulled and brought into the sensory lab. There, certified coffee graders perform cupping again, this time to ensure no quality loss occurred in transit. Moisture content, bean uniformity, and fragrance are retested. Beans that pass, these checks are tagged and routed to storage silos within the facility. These silos are food-grade, airtight steel vessels with internal climate regulation. Beans are stored based on variety, region, and intended blend. For example, Latin American beans destined for Starbucks blonde roast will be siloed separately from Ethiopian beans used in Starbucks Reserve offerings. Every silo is equipped with moisture sensors, thermometers, and pneumatic conveyor links, allowing operators to pull precise quantities for each roast batch according to master recipes. Before roasting can begin, beans are weighed into batches according to a specific ratio, depending on the blend being produced. Starbucks maintains an extensive library of proprietary blends, each with precise formulas. Some are single origin, where only one type of bean is used, while others, like Pike Place Roast or Espresso Roast, combine beans from multiple origins. Each blend is documented in the factory's recipe management software, which automatically calculates the needed amount of each component down to the gram and interfaces with weigh scale systems to ensure accuracy. At this point, the beans are ready for roasting, but that process is highly intricate and deserves its own full analysis. Starbucks does not simply roast coffee by applying heat until the beans turn brown. The next step involves drum roasters, roast curves, heat profiling, airflow modulation, and real-time chemical transformation monitoring that will take the green coffee and convert it into the rich, aromatic, deeply flavored roasted beans that Starbucks is known for worldwide. With the green coffee beans now housed in precision-monitored silos and organized by blend formulation, the next phase of Starbucks' industrial production process transitions into what is often regarded as the heart of the entire operation: roasting. This stage is where the true transformation begins. The raw, pale green beans, earthy, grassy, and flavorless in their original state, are subjected to meticulously calibrated heat treatments that unlock their signature color, aroma, body, and complexity. Starbucks takes this phase extremely seriously, investing in proprietary roast profiles, customized equipment, and a multi-layered monitoring system to ensure that every batch matches the company's highly specific taste standards. The roasting process begins when a batch of green beans is called for from the storage silos. These silos are directly connected to the roasting equipment via stainless steel pneumatic transfer tubes. When an operator initiates a roast cycle, a preset quantity of beans, anywhere from 100 to 600 kilograms, depending on the size of the roaster, is discharged from the silo and transported through vacuum-sealed lines to the roaster's holding hopper. Here, the beans are pre-weighed on industrial platform scales connected to the plant's central production database, ensuring the exact quantity is delivered as dictated by the roast formula for that specific product, whether it's French roast, Pike Place, Sumatra, or espresso. Starbucks uses drum roasters for most of its large-scale production. These roasters consist of a rotating steel drum with an internal blade assembly that keeps the beans in constant motion. This ensures even exposure to heat as the drum is gradually raised to operating temperature, typically ranging between 190 degrees Celsius and 240 degrees Celsius, depending on the roast level. Lighter roasts, such as blonde roast, are roasted to lower final temperatures, while darker roasts, like French or Italian, require longer exposure and higher terminal heat. The roasting process follows a specific curve known as a roast profile. This is a data-driven graph that plots time against temperature, representing how heat is applied across the roast cycle. Starbucks profiles are proprietary and tightly controlled, with each product requiring a unique curve to deliver its intended flavor profile. These curves are not linear. They involve temperature ramps, plateaus, and even controlled dips. The initial drying phase lasts for several minutes, during which moisture is driven out of the bean. This is followed by the Maillard reaction phase, where sugars and amino acids begin to react, producing the rich brown coloration and the first wave of complex aromas. The most critical moment in roasting is known as first crack. This is when internal pressure in the bean causes it to physically crack open, producing an audible popping sound, much like popcorn. This marks a key transformation in bean chemistry. Starbucks roast operators listen for this moment, using audio sensors and thermal feedback to identify it precisely. Lighter roasts may be completed shortly after first crack, while medium and dark roasts continue through the development phase, where oils begin to emerge on the surface and flavor compounds deepen. Throughout this process, the roaster's control panel displays live data for bean temperature, exhaust temperature, airflow rate, and drum speed. The system is equipped with PID controllers and data logging software that feed into the factory's centralized SCADA system. Every roast is archived digitally, allowing Starbucks to recreate identical roast profiles across facilities on different continents, ensuring global consistency. Once the beans reach their designated roast level, they are immediately discharged from the drum into a cooling tray located below the roaster. This tray contains a rotating arm assembly that stirs the beans, while powerful fans blow ambient or chilled air upward from perforated grates below. Rapid cooling is essential to halt the roasting process and lock in the intended flavor and roast depth. If the beans are allowed to remain hot too long, they may bake, resulting in a flat, dull cup profile. The entire roasting to cooling process for a batch of coffee typically takes between 10 and 15 minutes, depending on the desired roast level and bean origin. Once cooled, the roasted beans are conveyed into degassing hoppers, stainless steel holding vessels, where the coffee rests for a short period, usually 12 to 24 hours. This rest period is necessary to allow CO2, a natural byproduct of roasting, to escape. If roasted beans are packaged too soon, the trapped gas can compromise packaging seals or even cause bags to inflate and rupture. However, some CO2 is desirable, especially for brewing freshness, so the timing of degassing must be carefully controlled. During this resting period, samples of each roast batch are collected and sent to the on-site sensory lab. Here, trained cupping teams evaluate the beans using controlled brewing and tasting protocols. They assess key attributes like aroma, acidity, balance, mouthfeel, finish, and overall quality compared to Starbucks' master profile for that roast. Cupping is performed blind and in duplicate to eliminate bias and ensure accuracy. If a batch falls outside of the acceptable range, it may be blended with other batches to correct the profile, used for internal consumption, or in rare cases, discarded. Once a roast batch passes quality inspection, it is routed towards the grinding and packaging area. Some products, like whole bean offerings, will skip the grinding stage entirely, while others destined for ground coffee bags or capsules will be milled using precision grinders. These machines are fitted with hardened steel burrs or rollers that crush the beans to an exact particle size distribution. Starbucks defines specific grind profiles depending on brewing method. For example, drip coffee grind is coarser than espresso grind, and French press is coarser still. Grinding is a highly sensitive operation. During the process, friction from the burrs generates heat, which can degrade volatile aromatics if not carefully controlled. To counter this, industrial grinders are equipped with chilled air systems and thermocouple sensors that regulate burr temperature and prevent overheating. In many facilities, grinding is conducted in a temperature-controlled room or during cooler hours of the day to preserve freshness. As soon as the coffee is ground, it moves to packaging, often through vacuum-sealed transfer tubes that prevent oxidation. The packaging stage is designed to preserve flavor and aroma while ensuring shelf stability. Starbucks uses multi-layer barrier films for its ground coffee products. These films include aluminum or metallized polyester layers that block oxygen and moisture. Many packages are fitted with one-way degassing valves that allow CO2 to escape without letting oxygen in, protecting the coffee's integrity while preventing package ballooning. Packaging machinery includes vertical form fill-seal systems for smaller bags and horizontal form fill-seal machines for pillow packs or multi-packs. Each package is filled to a specific weight, sealed, and coded with production data, including roast date, location, shift, and lot number. High-speed check weighers and vision systems verify fill accuracy, seal integrity, and barcode clarity. Any package that fails inspection is automatically diverted off the line for rework. After packaging, the coffee products are grouped into cases and transferred to automated case packers and palletizers. Pallets are wrapped and labeled, then stored in temperature-controlled warehouses before shipping. These final steps, inventory control, cold chain monitoring, and outbound logistics, are critical to ensure the roasted Starbucks product reaches distribution centers and retail shelves around the world in optimal condition. With the coffee beans now expertly roasted, cooled, rested, and either packaged whole or ground and sealed, Starbucks' industrial production extends into another critical manufacturing domain, the preparation of its ready-to-drink beverages. These include bottled frappuccinos, chilled espresso drinks, cold brews, and dairy-based coffee blends. These products are not created in the same facilities that handle roasting and bagging. Instead, Starbucks partners with specialized beverage manufacturing facilities. Many cooperated with industry leaders like PepsiCo through the North American Coffee Partnership to manage this high-volume cold fill production. This stage involves liquid formulation, blending, thermal processing, homogenization, and sterile packaging under rigid food safety standards. The process begins with the formulation of the beverage base. For a bottled frappuccino, for example, this includes several core ingredients: brewed coffee extract, filtered water, sugar or corn syrup, dairy or dairy alternatives, stabilizers, and natural or artificial flavorings like vanilla, caramel, or mocha. Each component must be handled separately with precision before it's brought into the blending system. Coffee extract is typically delivered in concentrated form, produced by either brewing Starbucks beans at scale or using advanced extraction methods like cold concentrate percolation or high-pressure brewing. This extract arrives in refrigerated, food-grade totes or tanker trucks, depending on batch size. Upon arrival, it is sampled, analyzed for strength, and approved by the on-site quality control team before entering the liquid ingredient holding tanks. Simultaneously, dairy components such as milk and cream are received through chilled pipelines or aseptic bag-in-box systems. Dairy intake systems in Starbucks RTD plants are equipped with plate heat exchangers to quickly chill and store milk at temperatures below 4 degrees Celsius to maintain freshness and prevent bacterial growth. If using shelf-stable milk or UHT-treated dairy, the plant will still hold the product under cold storage until use. For plant-based SKUs, oat milk, almond milk, or soy milk are stored and handled in similar systems, albeit through dedicated lines to avoid allergen cross-contamination. Sweeteners and stabilizers such as sugar, corn syrup solids, carrageenan, cellulose gum, and pectin are weighed and pre-mixed in separate tanks. Starbucks beverages are engineered not just for taste, but for texture, mouthfeel, and visual consistency, especially in cream-based products like bottled mochas and vanilla frappuccinos. The stabilizers help suspend coffee solids, prevent dairy separation, and ensure the beverage maintains a smooth, homogeneous appearance on shelf, even after weeks or months in cold chain storage. All of these components, coffee extract, dairy or alternative milk, sweeteners, water, and flavor compounds, are brought together in the blending system. This usually consists of large stainless steel jacketed mixing tanks ranging from 1,000 to 5,000 liters. Each tank is equipped with an internal agitator, a bottom-mounted high-shear mixer, and in some cases, inline emulsifiers or homogenizers to ensure all elements are fully integrated. Tanks are fitted with load cells and flow meters, enabling automated dosing of each ingredient according to pre-programmed batch recipes. The blending system is monitored via a central control unit, typically a PLC-connected touchscreen interface that displays real-time values for temperature, mixing speed, pH, and ingredient flow. Operators can monitor the tank's temperature curve, the shear level during mixing, and the dwell time of each phase. In a typical Starbucks RTD batch, the blending cycle lasts between 30 and 60 minutes. During this time, inline sensors monitor turbidity, Brix, and viscosity. Samples are taken periodically to verify pH, flavor intensity, and microbial load before the batch is cleared for downstream processing. Once the beverage blend is complete and validated, the next stage is thermal processing. Most Starbucks RTD beverages are pasteurized using high-temperature, short-time systems, which allow for rapid heat treatment without compromising taste or texture. In HTST, the product is pumped through a heat exchanger that raises the liquid temperature to 85 degrees Celsius to 95 degrees Celsius for 15 to 30 seconds, then rapidly cools it to filling temperature, usually between 4 degrees Celsius and 10 degrees Celsius for cold fill lines, or slightly higher for hot fill bottles. This process effectively destroys any pathogenic microbes while preserving the coffee's aroma and flavor. Some facilities use ultra-high temperature processing for shelf-stable lines, allowing the product to remain unrefrigerated until opened. In UHT, the beverage is flash heated to temperatures up to 140 degrees Celsius for just a few seconds, then cooled quickly before packaging. The decision between HTST and UHT depends on the specific product's shelf life goals, packaging type, and distribution model. Immediately following thermal processing, the beverage passes through an inline homogenizer. This device applies intense pressure, often in excess of 2000 psi, to the liquid through a narrow valve, breaking down fat globules and suspended solids into microparticles. This step is critical for emulsion stability, preventing the cream from separating from the coffee or the flavor oils from rising to the surface. Homogenization also improves mouthfeel, making the beverage taste creamier and smoother. From here, the liquid is conveyed to the filling system. Starbucks RTD products are filled into a variety of package types: PET bottles, glass bottles, aluminum cans, and aseptic cartons. Each format requires its own dedicated filling and sealing system. For bottled frappuccinos, a cold fill rotary filler is typically used. This high-speed machine feeds sterilized bottles onto a rotating platform, where they are filled by gravity or volumetric fillers to exact fill levels. Immediately afterward, caps are applied, using steam-assisted capping heads to ensure a vacuum-tight seal and tamper resistance. Cans and cartons are filled on their respective lines, cartons often using form-fill-seal machines that shape the container, fill it, and seal the top in one continuous motion. All packages pass through automated detection systems that verify fill levels using weight sensors, check cap placement with vision systems, and scan barcodes to confirm packaging accuracy. Reject mechanisms immediately remove any container that fails these criteria. The filled beverages are then passed through a secondary cooling tunnel or refrigerated spiral conveyor that ensures they reach their final holding temperature before entering the packaging area. Depending on the product, this may be as low as 2 degrees Celsius, especially for refrigerated drinks destined for grocery and convenience store cold vaults. Once cooled, the individual containers are collected into multi-packs, shrink-wrapped, and placed into branded cartons. These cartons are then palletized by robotic arms and wrapped with plastic film. Each pallet is labeled with a unique identifier, linking it to the specific batch number, production date, filler line, and formulation ID. All of this information is uploaded into the factory's ERP system, providing full traceability from bean to bottle. Before any shipment is cleared, final product samples are pulled from each pallet for comprehensive testing. These include microbial testing, shelf stability stress tests, and sensory evaluations by trained panels. Only after all tests are passed are pallets released into refrigerated distribution channels for delivery to retail partners, Starbucks cafes, or direct-to-consumer platforms. From formulation and blending to pasteurization, homogenization, and ultra-clean packaging, this RTD production phase represents one of the most technologically advanced parts of Starbucks' global supply chain. It's where liquid meets logistics, combining industrial food science with tight controls over quality, taste, and branding. Every chilled bottle or can represents thousands of interconnected variables managed with absolute precision to deliver a consistent, enjoyable Starbucks experience anywhere in the world. With Starbucks ready-to-drink beverages now filled, sealed, chilled, and palletized, the focus shifts to the final, but no less complex, elements of factory operations. Sustainability integration, byproduct management, batch auditing, and outbound logistics. While the product may appear finished at this stage, the systems behind its release are still active, ensuring every bottle or can shipped reflects the brand's uncompromising quality, environmental responsibility, and traceability. One major component of this final phase is waste stream management. Every Starbucks beverage production facility is designed to minimize waste and make use of byproducts wherever possible. Coffee grounds remaining from extract production are collected and either sent to composting facilities, transformed into animal feed, or, in more advanced plants, used as biomass fuel to generate energy. Spent dairy materials or cleaning water are filtered and treated through on-site wastewater management systems, often returning grey water to municipal treatment plants within strict pH and chemical parameters. Packaging waste, including edge trims from shrink-wrap film, carton misprints, and PET bottle scrap, is separated and sent to in-factory compactors and balers. These bales are transported to certified recyclers for reprocessing. Starbucks has implemented programs at several manufacturing locations that convert unrecyclable soft plastics into composite shipping pallets or building materials, helping close the loop on production materials. In parallel with waste management, quality auditing continues even after packaging. Randomly selected finished products are pulled from every batch and routed to a dedicated quality assurance lab within the facility. There, they undergo another round of microbiological testing, sensory analysis, packaging integrity checks, and accelerated aging simulations. These simulations might involve storing the product at elevated temperatures for several days or weeks to mimic what could happen during prolonged distribution delays. Any deviation in flavor, appearance, or microbial safety can trigger a hold on the entire batch while root causes are investigated. All data generated, from roast date to filler head temperature, from pallet wrap tension to microbial test results, is logged in the facility's centralized manufacturing execution system. This digital record ensures that any shipment can be traced back through every step of the factory process. If a product recall is ever initiated, these logs allow immediate identification of affected units by date, location, and even by hour of production. When cleared, the finished pallets are scheduled for outbound logistics. Route planning software, inventory analytics, and order data from Starbucks' retail and grocery distribution teams are combined to determine where each batch will go. Products destined for grocery stores enter the cold chain system, transported in refrigerated trucks with temperature logs monitored in real time. Others, such as shelf-stable offerings, are routed to ambient storage hubs or export terminals for international shipping. In a modern Oreo manufacturing facility, key dry ingredients are delivered in bulk, often by rail cars or food-grade trucks, and are pneumatically conveyed into large storage silos made of stainless steel or epoxy-lined carbon steel. These silos are sealed from air and moisture and are connected to the factory's central control system. The main dry ingredients include unbleached, enriched wheat flour, processed cocoa powder, granulated sugar, and minor dry components like baking soda and salt. Each of these materials is handled in its own silo or hopper, and automated augers or vibratory feeders dispense precise quantities into batch weighing hoppers. These hoppers sit on load cells, sensitive scales that can measure down to a fraction of a gram. This is essential because the correct ratio of flour to cocoa to sugar directly affects not only the flavor, but also how the dough behaves under pressure during molding. If the cocoa content is even slightly too high, for instance, the dough may become too brittle and crack during forming. If it's too low, the wafers may bake up too soft, losing the crisp snap that defines an Oreo. Once the dry materials are batched, they are conveyed into a pre-mixing chamber. At this stage, powdered ingredients are briefly tumbled together to ensure initial homogeneity before liquids are added. Then it's time for the liquid components to enter the system. These include vegetable shortening, often a blend of palm and canola oil, along with a sugar syrup or glucose solution, invert sugar, lecithin, and vanillin or other flavoring agents. The fats and liquids are stored in temperature-controlled tanks and are metered into the mixer through heated pipes. The temperature of the fats is critical. Too cold, and they won't disperse evenly. Too hot, and they could melt too aggressively, breaking down the emulsion and affecting dough integrity. All of these components are combined in large jacketed horizontal mixers or double sigma arm batch mixers. These mixers are chosen for their ability to handle heavy, cohesive doughs while still ensuring thorough dispersion. Inside the mixer, paddles or blades knead the dough continuously, folding and stretching it to develop a uniform texture. The mixer operates under a specific time and speed profile, starting slow to incorporate the dry and wet components, then increasing speed to blend, then finishing with a gentle knead to avoid overworking the dough. The goal here is a dough that's soft but not sticky, cohesive but not tough. Sensors inside the mixing chamber monitor temperature and torque, two key indicators of dough readiness. If the dough becomes too warm from friction, it can become greasy and difficult to form clean edges in the molding machines. If it's undermixed, the ingredients won't be uniformly distributed, and inconsistencies in cookie size, color, and bake profile will result later on. Once the dough reaches its target specifications, it's discharged from the mixer through a hydraulically controlled trapdoor at the base of the mixing tank. The dough falls into a dough transport system, typically a set of conveyors or troughs lined with non-stick materials like Teflon or food-grade UHMW polyethylene. At this stage, the dough may still be slightly warm, around 30 degrees Celsius to 35 degrees Celsius, and has a dense, matte appearance with a strong cocoa aroma. Before moving to the forming machines, the dough must undergo a resting period in certain operations. This allows the flour to fully hydrate and any residual gases or trapped air to escape. In high-speed production environments, however, this rest period may be minimized or skipped altogether if the formulation is optimized for immediate processing. This completes the initial phase: ingredient intake, formulation, mixing, and dough discharge. Each step up to this point is carefully controlled by recipe management software that ensures no human error can affect batch consistency. Recipe locks, scanner-based operator identification, and redundant scale verification ensure each batch of Oreo wafer dough is made precisely to the specifications required to perform flawlessly in the next stage of the journey: shaping and embossing. Now that the chocolate wafer dough has been prepared with absolute precision, measured, mixed, and conditioned, it moves into one of the most visually iconic and mechanically fascinating phases in the Oreo production line: forming and molding. This step takes the dense, cocoa-rich dough and transforms it into thousands of uniformly sized, detailed cookie wafers, each embossed with the distinctive Oreo pattern. This is not simply cutting shapes out of dough, it's a highly engineered, high-speed process where consistency in shape, thickness, and surface detail must be maintained across millions of units every day. The freshly prepared dough is conveyed to a hopper positioned above a sheeter. This sheeter is a wide, stainless steel roller assembly that flattens the dough into a uniform sheet of specific thickness. The dough moves between a set of rollers, typically 2 or more steel cylinders calibrated to exact tolerances that compress it to the target height. For Oreo wafers, the final sheet is quite thin, often around 3 to 4 millimeters, with a consistent density and moisture distribution. Getting this thickness right is critical. If the sheet is too thick, the cookie may not bake evenly or could become too brittle. Too thin, and the cookies may crack, burn, or crumble during sandwiching. Sensors measure the thickness of the sheet continuously using laser or ultrasonic gauges. If deviations are detected, servo-driven actuators automatically adjust roller spacing to maintain precision. The sheeter also includes edge trimmers, small motorized blades that cut off uneven or frayed edges of the dough sheet to keep the line uniform. The trimmed edges are collected by a scrap recovery system and reintroduced into the mixing system, minimizing waste without compromising freshness or quality. Once the dough sheet is perfected, it enters the rotary molder. This machine is central to the Oreo brand's identity, as it forms the shape, size, and embossed design of each cookie wafer. The rotary molder consists of 2 primary components: a rotating die roller and a pressure roller. The die roller is a cylindrical drum engraved with multiple cavities, each one precisely carved with the Oreo design. These cavities aren't just cosmetic. Their depth and contour dictate the final relief of the cookie surface. As the dough sheet passes between the die roller and pressure roller, each cavity punches into the dough, compressing it into shape and imprinting the Oreo design. The pressure roller, covered in food-safe rubber or polymer, pushes the dough up into the die cavities, ensuring a clean, complete mold. As the die drum continues rotating, the shaped wafers are extracted by a combination of mechanical pushes and vacuum assist systems, which gently remove the cookies from the cavities without smudging the design. These freshly molded cookie wafers are then transferred onto a wide mesh conveyor belt in a continuous, uninterrupted line. Each wafer is spaced evenly to allow for proper airflow in the next phase, baking. Meanwhile, the excess dough surrounding the cutouts, known as webbing, is carefully separated and sent back through the scrap system. This recovery loop is highly efficient, capturing nearly 100% of the unused dough and returning it to the mixer via chilled transport belts. To ensure product consistency, reworked dough is blended at a fixed percentage into fresh dough, preventing any changes in texture, flavor, or moisture that might result from overprocessing. As the line of uniform, molded Oreo wafers advances, they approach the baking tunnel, one of the most thermodynamically sophisticated parts of the facility. The tunnel oven is a massive structure, often exceeding 30 meters in length, segmented into multiple temperature-controlled zones. Each zone is precisely tuned to manage the gradual dehydration and expansion of the cookie, ensuring even baking from edge to center. The ovens use convection, conduction, and in some cases, radiant heat, depending on the equipment manufacturer and regional factory specifications. The cookie wafers bake as they travel slowly through the tunnel, typically for a duration of 4 to 6 minutes. Conveyor speed, airflow rate, and internal oven temperatures are continuously adjusted via programmable logic controllers that interface with sensors monitoring internal humidity, surface temperature, and even color of the baking cookies using infrared imaging systems. The target bake is one where the cookie becomes crisp and fully set while retaining a slight moisture gradient at its core, enough to ensure it sandwiches cleanly without shattering, and holds up in milk without becoming soggy too quickly. Another crucial parameter monitored at this stage is cookie spread and diameter. Because the molded wafers expand slightly as they bake, their final size must fall within a fraction of a millimeter to ensure they'll match perfectly with their paired half during sandwiching. Edge blowout, where cookies develop uneven bulges or bubbles, is prevented by careful control of initial dough temperature, mold compression depth, and oven humidity during the first baking phase. As the cookies exit the oven, they are immediately passed through a staged cooling system. This phase is designed to gently bring the cookies from their internal post-bake temperature of roughly 160 degrees Celsius down to ambient room temperature. Cooling too quickly can cause the wafers to crack, warp, or experience checking, tiny surface fractures that affect aesthetics and structural integrity. To avoid this, the conveyor slowly moves the wafers through a series of cooling zones with progressively decreasing airflow temperatures. High-volume fans push filtered, dehumidified air over the wafers in a cross-flow pattern that cools them evenly on all sides. By the time the wafers reach the end of the cooling tunnel, they are firm, crisp, and at a stable moisture level, typically around 1.5% to 2%. This ensures maximum shelf life, a satisfying crunch, and ideal compatibility with the creme filling in the next phase of production. They are now ready for alignment and pairing. Wafers are automatically aligned into dual streams using diverters and channeling guides. Conveyor belts, equipped with vision systems, scan for defects such as missing embossing, chips, discoloration, or breakage. These systems use high-speed cameras and AI-assisted pattern recognition to detect any imperfections in milliseconds. Rejected cookies are diverted to a waste collection hopper, and approved wafers continue forward to the sandwiching stage. With the Oreo chocolate wafer cookies fully formed, baked, and cooled, the production line now transitions into one of the most iconic and mechanically synchronize parts of the process. Sandwiching. This stage involves the precise alignment of two delicate wafer halves around a carefully deposited swirl of creme filling, forming the complete Oreo cookie as we know it. What may seem like a simple task, placing filling between two cookies, is in fact a highly controlled and technically advanced process that prioritizes speed, accuracy, hygiene, and product consistency. The cooled wafers arrive at the sandwiching station via dual-lane conveyors that separate and feed cookies into two different orientations: bottom wafers and top wafers. The bottom wafers are destined to receive the cream filling, while the top wafers are held back momentarily, synchronized to arrive just as the filling has been deposited. Vision-guided pick-and-place arms or mechanical guides ensure that each cookie is properly positioned and oriented with the embossed design facing upward, especially important for branded recognition in the final presentation. The placement needs to be exact. Even a slight misalignment could result in uneven sandwiching or a crooked creme center, which would be rejected downstream. At the heart of the sandwiching line is the creme depositor. This component is engineered to dispense a precise amount of creme onto the center of each bottom wafer. The creme filling itself has been prepared earlier in the process and is stored in stainless steel holding tanks near the sandwiching line. The base creme is a blend of vegetable shortening, powdered sugar, and natural or artificial flavorings, aerated to achieve a smooth and creamy texture. It is kept at a controlled temperature, typically between 25 degrees Celsius and 30 degrees Celsius, to maintain flow consistency without being too runny or too firm. The creme is pumped into the depositor through a jacketed delivery line, which maintains temperature and prevents any hardening or separation. Inside the depositor, a rotary valve system or piston-driven nozzles release measured quantities of filling in circular swirls directly onto each passing wafer. The target deposition amount is extremely precise, usually around 3 grams per cookie for the original Oreo. For double stuff, the system is calibrated to deliver twice that volume, and the depositor nozzle height is adjusted accordingly to accommodate the larger swirl. The deposition speed is synchronized with the conveyor, meaning each swirl is deposited while the bottom wafer is in motion. To maintain consistent swirl shapes, the nozzle spins at a high RPM as it dispenses the cream. Sensors and imaging software track swirl size, height, and position. If the deposit strays from the central zone or falls outside weight tolerances, that cookie is automatically flagged and diverted. These sensors run continuously, sampling thousands of cookies per minute with extremely tight thresholds for variance. Once the creme is in place, the top wafer is gently placed onto the swirl. This is done by an overhead transfer arm or drop chute designed to lower each top cookie into place with just enough pressure to make contact without squashing the filling. The timing here is critical. Placing the top wafer too early could create smearing or incomplete adhesion, while placing it too late could allow the creme to set and result in a loosely held sandwich. Once the two halves make contact, a calibrated compression roller or paddle gently presses them together to create a uniform sandwich with a visible, even creme edge. The newly assembled Oreo cookies are then conveyed forward to undergo another round of quality inspection. At this stage, high-speed vision systems again scan for defects. These include cracked or broken wafers, misaligned sandwiches, off-center cream, or excess filling that has oozed out past the edges. Cookies that fail to meet standards are ejected via pneumatic pushers or retractable gates, landing in separate bins for non-conforming product. These rejected cookies are either discarded or recycled depending on factory policies and whether they passed earlier food safety checks. The good cookies move on to the next major phase, cooling and setting. Even though the creme filling is solid at room temperature, the act of depositing and sandwiching generates residual warmth, and the filling remains somewhat malleable for several minutes. To stabilize the sandwich structure and ensure long-term integrity during packaging and shipping, the cookies are passed through a controlled cooling tunnel. This tunnel gradually brings the product's temperature down to a stable point, typically just below ambient, which firms up the cream and locks in the sandwich's structural cohesion. As cookies exit the cooling tunnel, they are directed toward the packaging line. Here, the cookies are grouped and arranged into stacks or rows depending on the intended package format, whether it's a classic tray-style retail pack, a resealable pouch, a single-serving sleeve, or a multi-pack unit. For traditional packs, the cookies are guided into channels that group them into stacks, typically of 3 or more, which are then lowered into thermoformed plastic trays by robotic pick-and-place units. These trays help protect the cookies from damage and keep them organized for end-user convenience. Parallel to this, packaging film, pre-printed with branding, nutritional labels, and product information, is unwound from large rolls and fed into a form-fill seal machine. As the cookie-filled trays pass through the machine, the film is wrapped around the product, heat-sealed on all sides, and trimmed to size. Oxygen scavengers or desiccants may be inserted for freshness in some markets, depending on climate and shelf life requirements. For resealable packs, a Ziploc or peel-back adhesive strip is applied as part of the film sealing process, ensuring that consumers can open and close the package without reducing freshness. Each package unit is printed with a lot number, manufacturing date, facility code, and expiration date using high-speed thermal inkjet or laser printers. These codes enable full traceability and are cross-referenced with the production batch data stored in the factory's ERP system. From mixing and molding to creme filling and sealing, every step of the process can be traced back to specific machines, operators, shift schedules, and ingredient batches, an essential feature for food safety compliance and recall readiness. Once sealed, packages are conveyed to automated case packers. Here, robotic arms load the wrapped units into corrugated cardboard cartons, which are then glued or taped shut. These cartons are palletized according to preset patterns that optimize load stability and cube efficiency for shipping. Pallets are wrapped with stretch film, labeled with shipping barcodes and inventory data, and routed to the warehouse staging area. At this point, the Oreo cookies have completed their physical transformation from separate cocoa wafers and creme filling into a polished, fully packaged, ready-to-ship product. But before they leave the factory, they undergo a final quality audit. Samples from each batch are pulled from the finished goods line and tested by in-house sensory panels and laboratory staff. Taste, texture, aroma, appearance, and moisture content are evaluated to ensure that the product not only looks perfect, but delivers the consistent flavor and mouthfeel that Oreo is known for. Moisture levels are especially critical. Too high, and the cookie can lose its crispness during storage. Too low, and it can become brittle or stale. Texture analyzers apply mechanical pressure to the cookies to evaluate crunch resistance and breaking force, while gas chromatography is used to verify flavor compound profiles. Packaging integrity tests include drop tests, seal strength verification, and temperature cycling simulations that mimic transport and storage conditions across various markets. Once these final inspections are passed, the cookies are released for distribution. Pallets are loaded into climate-controlled trucks or containers, routed through regional distribution centers, and ultimately arrive at retail outlets, vending networks, or direct-to-consumer channels. With the Oreo cookie now fully assembled, inspected, packaged, and palletized, the final phase of the in-factory process is dedicated to the logistics, storage, inventory control, and outbound quality assurance systems that prepare the product for global distribution. While it may seem like the technical complexity is behind us, this stage involves its own set of sophisticated workflows designed to ensure that every package remains pristine, traceable, and shelf-stable for months after production, regardless of whether it ends up in a small, rural convenience store or a high-volume urban supermarket. The finished pallets of Oreos are moved from the end-of-line palletizing systems into a dedicated finished goods warehouse. This space is part of the factory complex, but isolated from production to prevent cross-contamination and maintain temperature and humidity stability. Oreo cookies, especially those with creme fillings, are highly sensitive to environmental changes. Excessive heat can soften the filling or compromise the packaging seal, while high humidity can cause moisture migration into the wafer, leading to loss of crispness. To combat these risks, the warehouse is maintained at a tightly regulated temperature, typically between 18 degrees Celsius and 22 degrees Celsius, with relative humidity kept under 50%. The facility is segmented into climate zones for different packaging formats, with certain areas reserved for international shipments that may require added humidity resistance or longer storage durations. Air handlers, industrial-grade dehumidifiers, and air filtration systems constantly regulate and cycle the air to maintain these parameters. Even the lighting systems are designed to minimize UV exposure, which could, over time, degrade packaging ink or food contact films. Once inside the warehouse, each pallet is scanned and logged into a warehouse management system. This system is fully integrated with the factory's enterprise resource planning software and allows operators to track not only where each pallet is stored, but exactly what production line, time, and ingredient lot was used to produce its contents. Each pallet label includes a unique serial number, barcode, and QR code that links to this full production history. This traceability is essential not just for internal logistics, but also for compliance with food safety regulations around the world, which require manufacturers to be able to track every product from raw ingredient to final point of sale. The WMS automatically arranges pallets by product type, batch date, and destination. Those scheduled for export may be routed to a separate staging zone where they will be checked for compliance with international packaging laws. Different markets may require translated labels, adjusted nutritional formats, or modified lot codes. Some export destinations also require additional tests, such as microbial swabs or accelerated shelf life sampling, to meet foreign government regulations. These are performed in an adjacent quality control annex, and only upon clearance are these pallets released to outbound logistics. Before any Oreo shipment leaves the facility, it undergoes a final visual inspection for physical damage to packaging, tamper seals, and box integrity. Any visible damage may indicate mishandling during internal transit or weak spots in pallet stability. Operators are trained to look for warped trays, compromised seals, or even small tears in the flow wrap film that could affect product freshness. Should any defect be discovered, that pallet is held for secondary inspection, and depending on severity, it may be repackaged or scrapped entirely. At this point, logistics coordinators use automated routing systems to schedule outbound shipments. These systems factor in geographic location, delivery deadlines, climate conditions, and truck availability. For example, shipments bound for warmer climates during the summer may be prioritized for insulated or refrigerated trucks to prevent the creme from softening. Long-haul shipments may be routed through distribution centers that offer cross-docking or climate-controlled storage to preserve product quality along the supply chain. The loading dock itself is operated with precision. Trucks arriving at the facility must be cleaned, inspected, and approved before any Oreo products are loaded. This includes visual inspection for pests, residue from prior shipments, and confirmation that the trailer temperature is within specification. Only after a truck passes these inspections does the facility open the dock door and begin the loading sequence. Robotic forklifts or human operators load the pallets according to pre-planned diagrams that ensure weight is evenly distributed and product is easily accessible at the destination. Each shipment is logged with time, driver ID, carrier information, route ID, and estimated delivery window. Once loaded, Trucks are sealed with tamper-evident locks and dispatched with digital shipping documents, including delivery confirmations and scanned QR codes for receiving teams. The WMS updates the ERP system in real time, closing the inventory loop and marking the batch as shipped. This inventory and logistics traceability is crucial for meeting compliance with global food safety standards like the Global Food Safety Initiative, hazard analysis and critical control points, and ISO 22000. Even after the Oreo product leaves the plant, the factory remains connected to its life cycle through digital feedback systems. Retailers and distributors have access to portal-based interfaces where they can report damages, delayed deliveries, or unexpected inventory issues. Returned products are scanned upon arrival at reverse logistics zones where factory staff investigate issues, analyze production records, and determine root causes. In cases where errors are found, such as premature staleness, flavor imbalance, or packaging failure, continuous improvement protocols are triggered to address the upstream causes. While these systems function to protect the product, they also feed into a broader factory goal: performance analytics and continuous optimization. The data from every shipment, temperature logs, shipping duration, breakage rates, seal integrity, and even consumer complaints is compiled into dashboards reviewed weekly by production leads, QA managers, and logistics coordinators. These dashboards enable the factory team to track KPIs like OTIF, defect per million rates, inventory turnover, spoilage reduction, and carbon footprint per pallet. Some Oreo plants are moving even further towards sustainability at this stage of production. Cardboard shipping boxes are made with recycled content and are themselves fully recyclable. Pallet wrap films are being downgauged or replaced with biodegradable alternatives. Facilities are experimenting with hybrid electric fleet partnerships or rail transport instead of trucks to reduce emissions. In select markets, even the plastic trays inside Oreo packs have been redesigned for recyclability, and clear labels now inform consumers on proper disposal.